Picture the night sky, that familiar canvas of twinkling lights you've gazed at your whole life. Now imagine if just one of those points of light wasn't a gentle, steady star like our own sun, but a true cosmic leviathan, a star so unimaginably vast that it could swallow our entire solar system and barely notice, a star where the very laws of physics seem to bend and scream under the weight of its own existence. This isn't science fiction. This is the reality of supermassive stars, the true titans of our universe. They possess a raw, terrifying power that makes our sun seem like a flickering candle in a hurricane, and their lives are a constant, violent rebellion against everything we thought we knew about how stars are supposed to behave. They are engines of creation and destruction on a scale so grand it defies human comprehension, and their strange, bizarre actions are rewriting the textbooks of astronomy right before our eyes. We are about to embark on a journey to the very edge of known physics, to explore 30 of the most peculiar, mind-bending behaviors these colossal objects exhibit. From stars that spin so fast they tear themselves apart to others that burp out vast clouds of their own guts or vanish into darkness without the courtesy of a supernova, the antics of these celestial giants are as bewildering as they are beautiful. Each one of these behaviors is a clue, a piece of a puzzle that points toward a deeper, more fundamental truth about the fabric of our cosmos. They challenge our most basic assumptions and force us to ask questions we never thought to ask, pushing the boundaries of human knowledge into territories that are both thrilling and humbling. So prepare to have your perspective on the universe permanently altered. What you are about to witness is not just a list of facts, but a revelation of the sheer, untamed drama unfolding in the depths of space, a drama where stars don't just shine. They perform acts of such strange and spectacular brilliance that they force us to reconsider our very place in the cosmos. This is the story of the universe's ultimate heavyweights and the 30 strangest ways they defy our understanding. Our journey into the strange behaviors of supermassive stars begins not with a gentle introduction, but with a display of cosmic self-destruction so grand it redefines the term unstable. We're talking about runaway hypergiants, a class of stars so absurdly massive that their very existence is a losing battle against themselves. Take VY Canis Majoris, for instance. If you were to place this star at the center of our own solar system, its surface would extend beyond the orbit of Jupiter, swallowing Mercury, Venus, Earth, and Mars in a fiery instant. But this isn't a stable, serene giant. It's a frantic, heaving beast perpetually on the verge of tearing itself to pieces. The core of this instability lies in a brutal civil war raging within the star. On one side, you have the unimaginable force of gravity, generated by the star's own tremendous mass, pulling everything inward with a grip that seems absolute. It is an unrelenting, crushing weight, constantly trying to compress the star into a smaller, denser object. Opposing this is the equally formidable power of radiation pressure. The nuclear fusion in the star's core is so ferociously intense that it generates a torrent of light, a literal flood of photons with so much energy that it pushes outward with tremendous force. In a normal star, these two titanic forces achieve a delicate balance, a stable truce that can last for billions of years. But in a runaway hypergiant, the balance is broken. The radiation pressure from within becomes so overwhelmingly powerful that it overcomes gravity's pull, and the star's outer layers are effectively blown away into space in colossal, chaotic eruptions. This is a star that is literally vomiting its own guts out into the void, shedding an Earth's worth of mass every single year in a desperate, violent attempt to stabilize. This ongoing, catastrophic mass loss doesn't just make these stars variable and unpredictable. It sculpts their immediate surroundings into some of the most spectacular structures in the galaxy. The material that is violently ejected doesn't just disappear. it forms vast, intricate nebulae that glow with the reflected light of the central star, like cosmic fingerprints of these titanic struggles. NML Cygni, another infamous hypergiant, is shrouded in a nebula so massive and complex it defies easy description, a churning cloud of gas and dust that the star itself has created from its own expelled body. These aren't the gentle, remnant clouds of a dead star. They are the ongoing, real-time evidence of a star fighting for its life, a beautiful and terrifying testament to the fact that even the largest objects in the universe are governed by forces they cannot always control. This constant shedding of mass is the first and most fundamental strange behavior, a dramatic demonstration that for some stars, being too big is a curse that leads to a short, spectacular, and violently unstable life. Now, if you thought a star slowly shedding its mass was dramatic, prepare yourself for a star that essentially decided to stage its own supernova preview and then forgot to finish the show. This brings us to the incredible case of Eta Carinae and the event known to astronomers as the Great Eruption. In the 1840s, this previously unremarkable star in the southern sky suddenly went berserk. Over a period of just a few years, it brightened explosively, becoming the second brightest star in the entire night sky, outshone only by Sirius. For a brief, brilliant moment, it was a beacon visible even in daylight, a celestial spectacle witnessed across the globe before it just as mysteriously faded away, leaving behind a profound and beautiful cosmic scar. That scar is the Homunculus Nebula, one of the most breathtaking and bizarre structures ever observed. When Eta Carinae erupted, it didn't just release a pulse of light. It blasted off an absolutely staggering amount of its own material, roughly 20 times the mass of our Sun, into the surrounding space. This ejected material didn't fly off in a random sphere, though. Instead, it formed two vast, opposing lobes of gas and dust that we see today as a magnificent, glowing hourglass. This nebula isn't something that formed over millennia. It is the direct, fossilized remnant of that single, violent tantrum from nearly 2 centuries ago. We are literally looking at the aftermath of a star's single, catastrophic outburst, frozen in time and expanding outward even now. A perfect laboratory for studying stellar death throes. And this is where the mystery deepens, because what exactly triggered the Great Eruption remains one of modern astronomy's most compelling puzzles. This was not a true supernova, the star survived. So what could possibly cause such a colossal, yet non-fatal explosion? The leading theory points directly to the fact that Eta Carinae is not one star, but two, locked in a deadly gravitational dance. It's a binary system with a primary star that is a hypergiant over 100 times the mass of our Sun, and a smaller, yet still incredibly powerful companion star. Astronomers suspect that as these two titans orbit each other on highly elliptical 5.5-year paths, their close encounters could create unimaginable instabilities. The prevailing idea is that as the stars swing perilously close, the gravitational pull of the smaller star may distort the bloated atmosphere of the larger one, literally pulling its outer layers away and triggering a massive eruption. Another possibility involves the two stars' powerful stellar winds, hurricanes of charged particles that stream from their surfaces, colliding with the force of billions of atomic bombs, creating such intense heat and pressure that the entire system becomes unstable. Eta Carinae is far from a quiet relic of the past. It is a cosmic time bomb, and everyone with a telescope is watching. The star remains highly unstable, showing wild fluctuations in brightness and constant activity. We know its days are numbered. A star this massive cannot last long. It is a prime candidate to go supernova, perhaps in our lifetimes, perhaps in 1,000 years. But its eventual, true death explosion will be a spectacle unlike any other in recorded human history. When it finally does explode, it will likely outshine the full moon, becoming visible in the daytime sky for months and casting shadows on the ground at night. It will be harmless to life on Earth, but it will be the greatest stellar show our planet has witnessed in all of human existence. Eta Carinae stands as a permanent reminder that the universe is not a static museum. It is a dynamic, violent, and ever-changing arena where stars can fake their own deaths, create art from their own chaos, and hold us in suspense for the final, breathtaking act. But this violent shedding of mass, as spectacular as it is, represents only one flavor of instability. For an even more extreme and erratic class of stars, we need to look at a specific, fleeting phase of stellar life known as the luminous blue variable. Imagine a star that doesn't just steadily lose mass, but one that experiences full-blown, violent identity crises, swelling and shrinking, brightening and dimming with a dramatic unpredictability that makes Eta Carinae look almost measured. These are the true divas of the cosmos, stars in their final, desperate act on the stellar stage, and their performances are both breathtaking and terrifying. The name itself, luminous blue variable, tells you almost everything you need to know. They are intensely luminous, often millions of times brighter than our sun. They are hot, which gives them a brilliant blue-white color, and most importantly, they are profoundly variable. Their instability isn't a gentle flicker. It's a series of monumental outbursts known as S-Doradus phases, named after the prototype star S-Doradus in the Large Magellanic Cloud. During one of these episodes, a star can increase its brightness by a factor of 10 or more and simultaneously expand its outer layers to a truly monstrous size. A star that was once a searingly hot, compact blue supergiant can, over a period of months or years, puff up into a much cooler, larger, and brighter yellow or even red hypergiant. It's as if the star is trying on different identities, unable to settle on what it wants to be before it dies. The physics behind this spectacular transformation is a story of a battle at the very edge of a star's endurance. It all comes back to the Eddington limit, a critical threshold in astrophysics. This is the point at which the radiation pressure generated by fusion in the core precisely balances the inward pull of gravity. For any star, this is the maximum stable luminosity it can achieve. Luminous blue variables lie perpetually on the very brink of this limit. Their cores are fusing elements at such an unimaginable rate that the outward push of radiation is almost strong enough to overcome gravity entirely. This creates a star that is perpetually on the verge of blowing itself apart. Its outer layers are so loosely bound by gravity and so intensely heated from below that they are essentially boiling. During a quiescent or quiet phase, the star manages to hold itself together, appearing as a hot blue object. But when the internal pressure builds past a certain point, the star can no longer contain itself. It doesn't explode in a supernova. Instead, it enters an S-Doradus outburst where it dramatically expands its surface area. By becoming larger and cooler, the star effectively reduces the radiation pressure at its surface, venting its immense energy in a slightly less efficient way and temporarily averting total self-destruction. It's a brilliant natural safety valve, but one that comes at the cost of its own stability. This cyclical swelling and contracting is far more than just a curious light show. It is a direct preview of the star's ultimate fate. Each violent outburst peels away another layer of the star's atmosphere, stripping it down and revealing deeper, hotter layers that were previously hidden. With every cycle, the star loses a significant portion of its mass, relentlessly carving away its own substance until it stands on the very threshold of its final cataclysm. A luminous blue variable is a star in the process of unmasking itself, shedding its outer veils until the bare, furious core is all that remains, ready to collapse. This phase is astronomically brief, lasting only a few tens of thousands of years, a mere blink in the multi-billion-year life of a star like our Sun. To witness a star in this state is to catch a rare and privileged glimpse of a cosmic metamorphosis, a tumultuous and beautiful struggle that signals the end is near. These stars are the universe's way of showing us that the final chapters of a giant's life are not a quiet fading, but a series of frantic, brilliant, and ultimately self-destructive convulsions. If the transformations of luminous blue variables feel like a star's desperate struggle for balance, then what comes next is the result of that struggle being lost, revealing a stellar core operating with terrifying, unrestrained power. We now enter the domain of the Wolf-Rayet star, a celestial entity so extreme it makes other supermassive stars look almost tame. Imagine a star that has effectively torn off its own skin, casting away its entire hydrogen-rich outer envelope to stand naked in the void. What remains is a blistering, exposed core, a furnace of fused helium, carbon, and oxygen, burning at temperatures that can exceed 200,000 degrees Kelvin. This is not a gentle giant, it is a stellar cannon firing a hurricane of its own substance into space at speeds that defy belief. The defining feature of a Wolf-Rayet star is its stellar wind, a relentless, supersonic gale of charged particles that streams from its surface. But to call it a wind is a profound understatement. This is not the gentle solar breeze our sun emits. This is a torrential, hypersonic blast. These winds can race outward at velocities approaching 3,000 kilometers per second, which is about 1% of the speed of light. To put that into perspective, a particle leaving a Wolf-Rayet star could travel from the Earth to the Moon in just over 2 minutes. This incredible speed is driven by the star's immense luminosity. The radiation pouring from the exposed core is so intense that it literally pushes the star's own atmosphere away, accelerating it to these phenomenal velocities. The result is a catastrophic, continuous mass loss that makes the eruptions of luminous blue variables seem almost leisurely. A typical Wolf-Rayet star can eject the mass of our entire sun in just 100,000 years, a rate 1 billion times greater than the solar wind. This ferocious outflow doesn't just disappear silently into the darkness. It slams into the slower-moving material that the star shed in its earlier, unstable phases, creating some of the most intricate and beautiful nebulae in the galaxy. These are known as Wolf-Rayet nebulae, and they glow with the intense energy of the collision. The fast-moving wind plows into the slower debris, compressing it and heating it until it fluoresces, much like a neon sign. The resulting structures are often delicate, bubble-like shells or elaborate pinwheel-shaped spirals, acting as a fossil record of the star's violent recent history. They are a visible testament to the sheer power being unleashed, a temporary tombstone being carved by the star itself. Ultimately, this self-cannibalization dictates the star's final, spectacular demise. By stripping away its hydrogen layers, the Wolf-Rayet star is prepping itself for a very specific kind of death. It is programming its own supernova. A star with a full hydrogen envelope will typically explode as a type Roman II supernova, but a Wolf-Rayet star, having shed that hydrogen, is a prime candidate for a different and often more energetic kind of explosion, a type Ib or Ike supernova. Furthermore, if the core of the star is massive enough and spinning rapidly, the collapse could produce the most violent event in the universe since the Big Bang, a long-duration gamma-ray burst. These are beams of pure, focused energy so powerful that if one were to occur within a few thousand light-years of Earth, it could sterilize the planet. The Wolf-Rayet phase is thus the final, critical act of self-sculpting. The relentless stellar wind is not just a spectacle, it is the chisel that determines the final form of the stellar corpse, whether it becomes a neutron star, a black hole, or the engine of a cosmic cataclysm that can be seen across the universe. Just when you thought the death of a star couldn't get any more dramatic, along comes a theoretical concept so violently absolute that it makes a black hole seem almost gentle. This is the fate reserved for the very heaviest of the heavyweights, stars that tip the cosmic scales at somewhere between 130 and 250 times the mass of our Sun. For these true monsters, a traditional supernova isn't enough. Their end is predicted to be something far more spectacular and final, a pair-instability supernova, an explosion of such unimaginable force that it scatters the star's entire being to the cosmic winds, leaving absolutely nothing behind. No neutron star, no black hole, not even a wisp of a remnant. It is the ultimate cosmic suicide. The chain reaction that leads to this utter annihilation begins deep within the star's core in its final moments. As such a colossal star nears the end of its life, it has fused a succession of elements in its central furnace, eventually creating a core of oxygen. Under normal circumstances, the fusion of oxygen would release energy and provide the outward radiation pressure needed to support the star against its own immense gravity. But here, the sheer mass of the star creates a catastrophic scenario. The core becomes so incredibly hot, soaring to billions of degrees, that the photons of light trapped within it are no longer just particles of light. They become packets of raw energy with a terrifying new power. When photons reach these extreme energies, they can spontaneously transform into pairs of matter and antimatter, specifically electrons and their antimatter counterparts, positrons. This spontaneous creation of particle-antiparticle pairs is the pivotal moment of doom. You see, radiation pressure, the very force that has been holding the star up, is provided by the relentless bouncing and pushing of these photons. When those photons suddenly convert into massive particles, that outward pressure dramatically and abruptly drops. It's as if the supporting pillars of a colossal building were instantly vaporized. With this pressure support gone, the balance of power shifts catastrophically to gravity, which now has an unchecked grip on the star's core. The core begins to collapse inward at a frightening speed. But this is not the collapse that forms a neutron star or a black hole. This implosion is the trigger for an even greater explosion. As the core violently contracts, it heats up to even more insane temperatures, to the point where oxygen fusion ignites almost everywhere at once. This isn't a controlled burn, it's a runaway thermonuclear bomb of stellar proportions. The energy released from this instantaneous oxygen fusion is so titanic that it doesn't just reverse the collapse, it completely overpowers the entire gravitational binding energy of the star. In a single, staggering pulse of energy, the entire star is utterly and completely torn apart. Every last atom, from the core to the outermost atmosphere, is blasted outward at velocities approaching 10% of the speed of light. The star doesn't just die, it is atomized, its entire mass flung back into the galactic reservoir to be used in future generations of stars and planets. It leaves a temporary, brilliant flash that can outshine an entire galaxy, and then nothing. A perfect and total erasure. While we have strong theoretical models for these events, catching one in the act has proven incredibly difficult, likely because they are so rare and occur in the early universe where the first stars were believed to be this massive. However, astronomers have spotted a handful of potential candidates in recent years. Supernova like SN 2007b, a colossal explosion that was significantly brighter and longer lasting than any ordinary supernova, fit the profile of a pair-instability event. These real-world observations are crucial because they provide a vital reality check for our most extreme stellar physics models, confirming that the universe is indeed capable of producing explosions of such absolute and final destructive power. This behavior represents the ultimate limit for stellar mass, a fundamental line in the sand drawn by the laws of physics. Cross it, and a star signs its own total and irrevocable death warrant, ensuring its legacy is not a dense corpse, but a magnificent, fleeting firework of pure, unadulterated energy. However, the universe is a place of fascinating nuance, and not every supermassive star is destined for such total self-annihilation. For stars that are massive, but perhaps not quite massive enough to cross the threshold into that ultimate oblivion, there exists a different, more protracted form of stellar agony. This is the realm of pulsational pair instability, a process where the star's end is not a single definitive blast, but a series of violent, earth-shattering convulsions, each one a prelude to a final collapse that is perpetually delayed. The underlying physics begins in the same terrifying place within a core that has become so intensely hot that photons of light spontaneously convert into electron and positron pairs. This conversion still causes a sudden, catastrophic drop in radiation pressure, triggering a collapse, but in this scenario, the star's mass is just below the critical limit for total disruption. So, when the core collapses and ignites runaway fusion, the resulting explosion is powerful, incredibly powerful, but it is not quite powerful enough to completely unbind the entire star. Instead of being utterly vaporized, the star experiences a massive partial eruption. The outer layers of the star are blasted away in a titanic pulse, ejecting many times the mass of our Sun into space, while the inner core survives, shaken but still intact. What happens next is what makes this behavior so strange and cyclical. After this first gigantic pulse, the star, now having shed a significant portion of its mass, actually settles down for a period. The core, exposed and now under less pressure from the overlying layers, resumes its fusion processes. It continues burning, building up a new inventory of heavy elements, and the cycle begins anew. Over centuries or millennia, the core heats up once more, reaches the pair-instability threshold again, and triggers another colossal pulse eruption. The star effectively becomes a cosmic geyser, erupting in these monstrous bursts every time its internal pressure cooker reaches a critical point. Each pulse strips away another chunk of its atmosphere, sometimes 5, 10, or even 20 solar masses at a time, slowly whittling the star down to its core. The aftermath of this stop-start self-destruction is written in the intricate structures surrounding the star. Unlike the single, homogeneous shell of a typical supernova remnant, a star undergoing pulsational pair-instability creates a series of nested onion-like layers. Each major eruption sends a shell of material racing outward. The next eruption then sends another shell plowing into the first, creating a complex circumstellar environment of interacting shocks and glowing gas. Astronomers observing such an object wouldn't see a clean, simple nebula. They would see multiple distinct shells of material, each representing a separate, violent tantrum in the star's final centuries. This layered history provides a forensic record of the star's death throes, a timeline of instability frozen in expanding gas. This protracted death dance has profound implications for the star's ultimate fate. By repeatedly shedding its outer mass, the star is essentially lowering its own final weight class. Each pulse brings its core mass down until it finally falls below the threshold for pair-instability entirely. Once this happens, the pulsations cease. The now exposed core, stripped of its massive envelope, continues its fusion journey until it finally runs out of fuel and collapses in a more traditional, though still spectacular, core collapse supernova. The final explosion, therefore, happens in a star that is far less massive than it was at the start of its pulsational phase. This can produce a supernova with a peculiar chemical signature, one that shows evidence of multiple episodes of mass loss and layers of different elements ejected at different times. In this way, pulsational pair-instability acts as a cosmic regulator, a drawn-out and violent process that prevents some stars from reaching the absolute limit of stellar existence, forcing them to shed their grandeur in a series of explosive fits before they are finally permitted to die. Yet, even amidst these predictable cycles of pulsation and collapse, the universe holds in reserve one of its most deceptive cosmic performances, a class of events so brilliant they can masquerade as the final death of a star, only for the star itself to emerge from the glare, wounded but very much alive. These are the supernova imposters, spectacular outbursts that borrow the radiance of true stellar death while being, in reality, nothing more than a star's cry of existential distress. They challenge the very definition of a supernova, forcing astronomers to ask a profound question. How can we be sure a star has truly died when we witness a cataclysm from billions of light years away? The key to this celestial deception lies in the sheer scale of the eruption. A typical imposter event, such as the stunning outburst observed in the galaxy NGC 3432 in 2009, can release a phenomenal amount of energy, causing the star's brightness to increase by a factor of hundreds or even thousands. For weeks or months, it shines with the ferocious intensity of a true core collapse supernova, outshining every other star in its host galaxy and becoming visible across intergalactic space. To any telescope scanning the skies, it appears as just another supernova, a point of light where none was before, signaling the violent end of a massive star. The initial data checks all the boxes: a massive star progenitor identified in pre-explosion images, a brilliant ultraviolet flash, and a slow, lingering fade. It walks like a supernova and talks like a supernova, but then something extraordinary happens. Instead of fading into permanent darkness, the light curve plateaus, and over the following years, the brilliant object doesn't vanish. It remains. Follow-up observations with powerful telescopes like Hubble eventually reveal the shocking truth: the star is still there. It survived. What was witnessed was not a death, but a near-death experience. So what physical mechanism could possibly produce such an immense blast without completely destroying the star? The answer circles back to the same extreme instabilities we see in luminous blue variables and hypergiants, but pushed to an even more violent extreme. An imposter event is essentially a super eruption, a giant stellar belch on a truly apocalyptic scale. In these outbursts, the star does not just shed a small amount of mass, it ejects a substantial fraction of its own envelope, sometimes several solar masses worth of material, in a single explosive episode. This colossal shell of gas is blasted outward, but at velocities slower than a true supernova blast wave. As this ejected material expands, it heats up due to its own internal shocks and the intense radiation from the battered but surviving stellar core. The resulting glow is what produces the brilliant, sustained flash that so perfectly mimics a supernova. It is the light of the star's own flesh, torn away and set ablaze in space. This phenomenon offers astronomers an invaluable, almost miraculous opportunity. A true supernova is a one-way ticket. The star is gone, and we can only study its expanding remains. But a supernova imposter is a live dissection. Because the star survives, we can observe it both before and after its cataclysmic tantrum. By studying the star in the aftermath, we can analyze the composition of the ejected material, which provides a direct sample of the inner layers of the star that were previously hidden from view. This is like a geologist being able to analyze the Earth's mantle after a volcanic eruption without having to dig a hole. The imposter event in NGC 3432, for instance, provided a pristine laboratory to study the final, frantic phases of mass loss that precede a star's actual core collapse. It revealed that the star was surrounded by dense, complex shells of material it had ejected in previous, quieter outbursts, painting a picture of a star in constant, violent turmoil in the millennia before its ultimate demise. The existence of these imposters forces a significant revision of our stellar life cycle models. They demonstrate that the final journey toward supernova is not a quiet, stately procession but a stuttering, erratic stumble, punctuated by these brilliant false alarms. Each imposter event is a desperate attempt by the star to achieve stability by shedding its excess mass, a process that profoundly shapes the environment into which the final, real supernova will eventually explode. When that true death blast does occur, it will expand into a space already cluttered with these earlier ejecta, leading to a brighter, more complex, and longer-lasting supernova remnant. In this way, the supernova imposter is not merely a fascinating oddity. It is a crucial prelude, a dramatic dress rehearsal for the main event that provides a living, breathing test subject for the most violent processes in a star's life. While we've been exploring stars tearing themselves apart from within, there exists another class of cosmic giants that are victims of a different kind of violence, a violence so immense it can fling an entire star across the galaxy like a stone from a slingshot. We are entering the realm of the hypervelocity runaway stars, stellar titans traveling at such phenomenal speeds that they are effectively escaping the gravitational pull of the Milky Way itself. To understand their story, we can look to Eta Carinae, a brilliant blue giant streaking through space, whose turbulent journey paints a vivid picture of stellar cataclysm and cosmic abandonment. Eta Carinae is a behemoth, a star about 20 times the mass of our Sun, and it is not merely drifting through its galactic neighborhood. It is racing through the void at a staggering velocity of roughly 30,000 kilometers per hour, a speed so great it would take you less than 5 seconds to circle the entire Earth. This isn't a gentle cruise, it's a headlong, desperate flight. But how does a star, an object of such immense mass, attain such incredible speed? The leading theory is as dramatic as it is tragic, a story of a broken celestial partnership. The most compelling explanation is that Eta Carinae was not always alone. It was once one half of a binary star system, two massive stars locked in a mutual orbit, destined to live and die together. The catastrophe began when its companion star, an even more massive and shorter-lived giant, reached the end of its life and exploded as a supernova. The physics of this stellar ejection is a masterclass in cosmic violence. In a stable binary system, the two stars orbit around a common center of mass. When one of them goes supernova, the explosion is not symmetrical. It's a chaotic, asymmetric event. If the exploding star blows off its outer layers in a lopsided fashion, the collapsing core can receive a powerful kick from neutrinos and other processes, sending the newly formed neutron star or black hole careening off in one direction at high speed. This sudden, violent removal of roughly half the system's mass is the key. The binary's gravitational bond is instantly and catastrophically severed. The surviving star, Eta Carinae in this scenario, is suddenly freed from its orbital tether. Like a ball on a string when the string is cut, it flies off in a straight line, inheriting its original orbital velocity while its gravitational anchor has vanished. It is flung out into the galaxy, a lone survivor of a monumental disaster, carrying with it the orbital momentum of its former life. The evidence for this dramatic history is written not just in the star's motion, but in the spectacular environment surrounding it. As Eta Carinae plows through the galaxy, it doesn't travel through a perfect vacuum. It encounters the thin, diffuse clouds of gas and dust that populate interstellar space. The star, despite its journey, is still a powerful entity, emitting a fierce stellar wind, a continuous stream of charged particles flowing from its surface. This wind slams directly into the interstellar medium ahead of the star, and the result is a breathtaking structure known as a bow shock. Think of the wave that piles up in front of a speedboat as it cuts through the water. Eta Carinae creates a cosmic version of this. The colliding material is compressed and heated, causing it to glow in brilliant infrared light, forming a vast, arcing shield that appears to spearhead the star's frantic passage. This bow shock is a perfect, glowing signature of the star's hypervelocity, a monumental ripple in the fabric of space that announces its traumatic past to anyone who can see it. It is the permanent, beautiful scar of its escape. The existence of these runaway stars has profound implications for our understanding of galactic ecology. They are celestial pilgrims carrying the elemental ingredients of their birthplaces across vast distances. A star like Eta Carinae, forged in a dense, metal-rich stellar nursery, is now seeding the more barren, outer regions of the galaxy with heavy elements through its powerful winds. It is a pollinator on an interstellar scale, enriching pockets of the galaxy that might otherwise remain pristine. Furthermore, by tracing the paths of these runaway stars backward, astronomers can attempt to pinpoint their place of origin, often leading them back to known supernova remnants or dense star clusters, effectively solving cosmic cold cases. These stellar fugitives are more than just curiosities. They are active, dynamic agents of chemical distribution, and their solitary, high-speed journeys ensure that the story of their violent birth continues to shape the galaxy they race through. Just when you think you've catalogued every possible form of stellar drama, the universe reveals a star that doesn't explode or erupt but simply vanishes. Not with a bang, but with a whisper. These are the Eta Carinae borealis variables, a rare and enigmatic class of supergiant stars that engage in one of the most perplexing acts of cosmic hide and seek ever observed. Unlike the violent, bright outbursts of hypergiants, these stars do the exact opposite. Without any warning, their brilliant light can suddenly plummet, fading by a factor of 100 or even 1,000, sometimes in a matter of weeks. They don't just get a little dimmer, they can almost disappear from the sky, only to slowly, mysteriously, return to their former glory months or years later. It's a cycle of dramatic dimming and re-brightening that seems to defy the very nature of what a star is: a stable source of light. The key to unraveling this mystery lies in the unique and bizarre composition of these stars. While virtually every other star in the universe is overwhelmingly made of hydrogen, the most abundant element, Eta Carinae borealis stars, are chemical freaks. They are profoundly hydrogen deficient. Their atmospheres are instead dominated by helium and, even more strangely, carbon. They are, in essence, massive orbs of soot. This peculiar chemistry is the crucial clue pointing toward a strange and violent origin story. Astronomers believe these stars are not born this way, but are created through stellar mergers, the cataclysmic collision and mixing of two older stars, like a white dwarf and a helium-burning star, which scrambles their internal chemistry and blows away the outer hydrogen layer. The result is a newborn supergiant with an atmosphere rich in the ash of nuclear fusion, a stellar phoenix risen from a violent union and now behaving in ways no single star ever could. So how does a carbon-rich atmosphere lead to such sudden, unpredictable blackouts? The leading explanation is as elegant as it is strange. It's the soot model. Imagine the star's upper atmosphere as a vast, hot and turbulent region. Under normal conditions, it's a gaseous haze transparent to the star's intense light. But occasionally, when the temperature and pressure in certain patches of the atmosphere dip just enough, a remarkable phase change occurs. The carbon atoms, which are normally suspended individually in the gas, suddenly begin to clump together. They nucleate, forming microscopic particles of solid carbon, essentially specks of soot. This is not unlike the process of water vapor in our own atmosphere condensing into clouds, but here it's a cloud of pure carbon dust forming right at the edge of a searingly hot star. Once this condensation begins, it can trigger a runaway effect. These newly formed carbon dust grains are incredibly effective at absorbing light. As they absorb the star's radiation, they are pushed outward by the relentless pressure of that same starlight. This radiation pressure accelerates the soot, driving it away from the star and causing more carbon to condense in its wake. In a remarkably short time, a colossal, opaque cloud of carbon dust can form high in the star's atmosphere, a vast, dark shroud that billows out and completely blocks our view of the stellar surface. From our perspective, the star hasn't changed. It's still shining just as brightly as ever. But its light is now being absorbed by this internal curtain of soot, which heats up and re-radiates the energy as invisible infrared light. To our optical telescopes, the star has effectively been switched off. The recovery from this stellar blackout is just as fascinating as the fade itself. The shroud of carbon dust isn't permanent. It's a tenuous cloud, not a solid object, and it continues to be pushed outward by the star's relentless radiation pressure. Eventually, the cloud expands, thins out, and dissipates into the surrounding interstellar space. As it does, the blanket is lifted, and the star's brilliant light once again streams through unimpeded. slowly returning to its normal brightness over a period of months. The cycle is then complete, ready to begin again at a moment's notice. There is no regular schedule for these events. An Eta Carinae borealis star might experience several fades in a decade, or it might remain bright for many years before suddenly deciding to dim again. This unpredictability makes them maddening and captivating to observe, as you never know when one will next decide to perform its signature disappearing act. But of course, the universe is a master of creating stars that defy simple categorization, and nowhere is this more evident than in the bizarre case of the yellow hypergiants. Imagine a star caught in a cosmic tug-of-war, too massive to be stable but desperately trying to find a comfortable identity, and you'll begin to understand this peculiar class of object. Their strangeness is so profound that astronomers have given their unstable state a forbidding name, the yellow evolutionary void. This isn't just a region on a chart, it's a theoretical danger zone for supermassive stars, a place of such extreme instability that no star is expected to remain there for long. It represents a brief, violent, and transitional phase in a giant's life, a frantic scramble between two more stable states that often ends in catastrophe. To visualize this, picture the Hertzsprung-Russell diagram, the fundamental map that astronomers use to classify stars by their temperature and luminosity. On one side, you have the hot blue hypergiants, like the luminous blue variables we discussed earlier, blazing away with ferocious intensity. On the other side, you have the cool, vast, and inflated red supergiants like Betelgeuse, massive but in a different, more sedate way. The yellow hypergiants exist in a precarious no-man's land right between them. Their surface temperatures are similar to our Sun's, giving them a characteristic yellow hue, but their sheer size makes them hundreds of thousands of times more luminous. This middle ground is the void, and the reason it's so unstable comes down to the star's outer layers. In this temperature range, the star's atmosphere becomes partially ionized, meaning it becomes incredibly opaque to its own light. This opacity traps radiation with fearsome efficiency, causing the outer layers to heat up, expand, and become so loosely bound that even a slight nudge can trigger a massive ejection of material. The star becomes its own worst enemy, physically unable to maintain a steady state in this particular configuration. To witness the dramatic consequences of this instability, we need look no further than Rho Cassiopeiae, a true diva of the northern sky and the prototypical yellow hypergiant. Located about 8,000 light-years away, this star is a behemoth, roughly 500 times the diameter of our Sun. For decades, astronomers have watched Rho Cassiopeiae with a mixture of awe and apprehension, as it is a master of the dramatic, unpredictable performance. Its most famous act occurred in the year 2000, when it did something almost unheard of for a star of its class. Over a period of just a few months, its visible brightness plummeted, and its surface temperature appeared to swing wildly. But this wasn't a simple dimming, this was a full-scale eruption. Rho Cassiopeiae had ejected a colossal amount of material, roughly 10,000 times the mass of Earth, or about 3% of our Sun's entire mass, in a single, violent outburst. This wasn't a gentle stellar wind, it was a titanic belch of the star's own atmosphere, an event that literally threw off a shell of gas with enough force to momentarily obscure the star itself. The mechanics behind this eruption are a direct result of the star's battle with the yellow void. The trapped radiation in its inflated atmosphere built up so much pressure that the star could no longer contain itself. The outer layers, already teetering on the edge of stability, were literally blown off into space. As this enormous shell of hot gas expanded and cooled, it did two things. First, it temporarily dimmed the star's light, much like the soot clouds of an Eta Carinae borealis variable. Second, and more importantly, the act of ejecting this mass had a profound effect on the star's internal structure. By shedding its outer, cooler layers, Rho Cassiopeiae effectively peeled back its own skin, revealing the hotter, denser layers beneath. This caused the star's apparent surface temperature to skyrocket, pushing it back toward the blue side of the void. It was as if the star, in a single convulsive effort, tried to escape its yellow prison and become a blue hypergiant again. This frantic bouncing back and forth is the defining characteristic of a star trapped in the evolutionary void. It's a cyclical, self-correcting, and self-destructive process. A star might swell into the yellow void from the blue side, become unstable, erupt to shed mass, and heat up to become blue again. Alternatively, a red supergiant might contract and heat up into the yellow zone, only to find the environment so hostile that it erupts and may even fall back toward the red. Each passage through this unstable region is marked by these violent outbursts, with each eruption peeling away another layer of the star's substance and driving its ultimate evolution. The duration of this phase is astronomically brief, perhaps only 10,000 years, a mere instant in a star's multi-million-year life. To observe a yellow hypergiant like Rho Cassiopeiae is to catch a star in a moment of profound identity crisis, a fleeting but spectacular struggle that dramatically shapes its final journey toward supernova. These stars are living proof that in the cosmic arena, the path of evolution is not always a smooth transition, but can be a violent, chaotic, and breathtakingly beautiful series of fits and starts. Now, if you thought a star being flung across the galaxy or one shrouding itself in soot was extreme, consider a stellar death so violent it doesn't just leave behind a corpse, but forges the universe's most powerful permanent magnet, an object of such concentrated fury that it can crack its own crust and send ripples through the fabric of spacetime itself. This is the destiny for a specific class of supermassive stars, those that not only possess tremendous mass but also spin at a ferocious rate, and their final act gives birth to the magnetar, a neutron star with a magnetic field so strong it fundamentally warps the very nature of reality around it. To understand how such an object comes to be, we need to rewind to the final moments of its progenitor star. Picture a stellar core that is not only incredibly massive, perhaps 25 to 40 times the mass of our Sun, but also rotating incredibly fast. This rapid spin is the crucial ingredient. As this colossal core runs out of nuclear fuel, the inward crush of gravity becomes unstoppable. In a fraction of a second, the core collapses from a sphere thousands of kilometers wide down to a city-sized ball of neutrons just 20 kilometers across. This is where the magic, or rather the terrifying physics, happens. In any collapsing system, fundamental properties like conservation of angular momentum, the same principle that causes an ice skater to spin faster when they pull their arms in, go into overdrive. The star's initial fast spin is amplified astronomically as it shrinks, just like that ice skater pulling into a dizzying pirouette. Simultaneously, the magnetic field lines that were threaded through the original star get squeezed and concentrated within this suddenly tiny, incredibly dense object. This dual amplification process is like taking a modest bar magnet and compressing it into a pinpoint, supercharging its magnetic power to almost unimaginable levels. The result is a newborn neutron star born spinning hundreds of times per second and possessing a magnetic field measuring a staggering 10 to the 15th power Gauss. To put that number in perspective, Earth's magnetic field is about 1 Gauss. An MRI machine operates at around 10,000 Gauss. A magnetar's field is a quadrillion times stronger than our planet's. This is a level of magnetism so intense that it can actually bend and distort the atoms that make up the star's own crust, and in a vacuum, it would be strong enough to strip the information right off a credit card from 100,000 kilometers away. This unimaginable magnetic stress doesn't just sit there quietly. It has catastrophic consequences for the magnetar's solid crust. A neutron star isn't a gaseous ball. It has a solid, incredibly hard surface of iron nuclei locked in a crystalline lattice. But this crust is pinned to the swirling, superfluid neutron interior below. As the magnetar's immense magnetic field gradually slows its rotation over time, a process known as magnetic braking, the crust is forced to adjust. The problem is, the crust is rigid and it can't always deform smoothly. The stress builds and builds until, finally, the crust fractures. This event is a starquake, a seismic shudder on a scale that makes any earthly earthquake seem like a gentle tremor. The energy released in a single, sudden crustal shift is titanic, greater than the total energy output of our Sun over 100,000 years. It is this catastrophic cracking that is believed to be the engine behind the magnetar's most famous and frightening phenomenon, the giant flare. When one of these starquakes occurs, it violently shakes the magnetar's insanely powerful magnetic field. This is analogous to the way moving a magnet near a coil of wire generates an electric current, but amplified to a cosmic, terrifying degree. The seismic energy is converted directly into a blast of electromagnetic radiation, primarily in the form of gamma rays and X-rays. For a brief, blinding moment, the magnetar can become the brightest object in the entire gamma-ray sky, outshining every other gamma-ray source in the universe combined, including all the other stars and galaxies. The flash from a giant flare is so luminous that if one were to occur within 10,000 light-years of Earth, it would temporarily outshine the full moon, and its pulse of radiation would significantly ionize our planet's upper atmosphere, potentially damaging satellites and disrupting global communications. We have witnessed a handful of these events from magnetars in our own galaxy, each one a stark reminder of the barely contained fury lurking within these dormant-looking stellar cinders. The existence of magnetars, therefore, gives us a profound insight into the chaotic conditions of a supermassive star's final collapse. They are not just random cosmic oddities, they are the direct descendants of a very specific type of star, one that was massive enough to form a neutron star, and critically, one that was spinning fast enough to amplify its magnetic field to these epic proportions during its death throes. Every magnetar we detect is a fossil record of a star that lived fast, died young, and left behind the most magnetically violent corpse in the cosmos, a permanent testament to the fact that a star's spin is just as important as its mass in determining the strange and powerful legacy it leaves behind. But the sheer explosive power of a magnetar, immense as it is, pales in comparison to a cosmic event that serves as the universe's ultimate exclamation point, a gamma-ray burst. These are not mere stellar explosions, they are focused beams of pure energy, the single most luminous events we have ever witnessed, capable of releasing more energy in 10 seconds than our Sun will over its entire 10 billion-year lifetime. And at the heart of these incomprehensible blasts lies one of the most extreme and finely tuned stellar death scenarios imaginable, involving a very specific type of supermassive star known as a collapsar. The story of a long-duration gamma-ray burst begins with a stellar titan that is both massive and a rapid rotator. We're talking about a Wolf-Rayet star, one that has already shed its hydrogen envelope, leaving behind a bare, spinning core of helium and heavier elements. This core is colossal, likely weighing in at over 30 times the mass of our Sun. And it's this combination of tremendous mass and rapid spin that sets the stage for a uniquely catastrophic collapse. When this star finally exhausts its nuclear fuel, the core can no longer support itself against gravity and begins its fatal implosion. In a more ordinary, slowly spinning star, this collapse would result in a standard core collapse supernova, perhaps leaving behind a neutron star or a black hole. But in a collapsar, the rapid rotation changes everything. It acts like a centrifugal brake, preventing the infalling material from plunging directly into the nascent black hole at the center. Instead of a chaotic, spherical collapse, the material forms a vast, swirling disk of superheated gas, an accretion disk, that orbits the newborn black hole at velocities approaching the speed of light. This is not a placid, gentle disk like Saturn's rings. This is a hyper-accreting torus of matter, a maelstrom of unimaginable violence where friction and magnetic fields heat the gas to billions of degrees. Material from the inner edge of this disk is devoured by the black hole, but thanks to the physics of extreme gravity and rotation, not all of it can cross the event horizon. A significant fraction of the inrushing matter, along with an immense amount of energy, is instead funneled and focused by the black hole's powerful magnetic fields and its own rotation. This energy is channeled upward and downward, away from the accretion disk's poles, and launched into space in the form of two opposing, highly collimated jets. These are not jets of slow-moving gas. They are beams of plasma accelerated to more than 99.9% of the speed of light. They are, in essence, relativistic blowtorches that drill their way out through the collapsing star's outer layers, punching through in a matter of seconds. And here lies the most critical factor that determines whether we on Earth witness this event as a gamma-ray burst: the orientation. The entire phenomenal output of this cosmic engine is concentrated into two incredibly narrow beams. If one of those jets is pointed directly at our solar system, then we see the full, terrifying brunt of its energy. For those few precious seconds, that pinpoint of light in a distant galaxy can outshine every star, every quasar, every other source of light in the entire observable universe combined. It is a flash of high-energy gamma rays so intense it can be detected by satellites billions of light-years away. If the jets are pointed in any other direction, we would see nothing out of the ordinary, perhaps just a faint, unremarkable supernova in a distant galaxy. Our entire perception of this ultimate cosmic cataclysm depends entirely on our chance alignment with its axis of destruction. The aftermath of the initial blast is just as telling. The long duration in the name refers to bursts that last from 2 seconds to several minutes, and this prolonged emission is a direct result of the central engine's activity. The hyper-accreting black hole doesn't shut off instantly. It can continue to feed on the surrounding stellar material for tens of seconds, persistently powering the jets and creating the sustained flash we observe. Once the jets have broken free and the central engine finally sputters out, we are left with a fading afterglow that can be seen across the electromagnetic spectrum, from X-rays to radio waves. This afterglow is created as the relativistic jets plow into the tenuous gas of the interstellar medium, creating a shockwave that continues to glow for days or weeks. It is this lingering echo that allows astronomers to pinpoint the burst's host galaxy and confirm its association with the death of a massive star in a region of active star formation. Understanding this mechanism fundamentally changed our view of stellar death. It revealed that a supernova is not always the final word. For the most massive, rapidly spinning stars, it can be merely a side effect of the true main event, the birth of a black hole engine that can, for a brief moment, outshine the rest of the cosmos. The collapsar model elegantly ties together the need for a massive stellar core to form a black hole, rapid rotation to create the accretion disk and jets, and the loss of the hydrogen envelope to allow those jets to escape without being smothered. It is a recipe for destruction of such precise and extreme conditions that it explains why gamma-ray bursts are so phenomenally rare in any given galaxy. They represent the ultimate expression of a star's death, a final, focused scream of energy that announces the creation of a new black hole across the vast expanse of space and time. And just when the universe seems to have exhausted its catalogue of stellar violence, it reveals a phenomenon where even the single most energetic explosion known, a supernova, isn't chaotic but rhythmic. We are now observing behavior 13, quasi-periodic pulsations in supernova. Imagine witnessing a city-leveling bomb blast, but instead of a single, deafening roar, you hear a distinct, repeating drumbeat within the explosion. This is the baffling reality astronomers have begun to document, a regular flickering superimposed on the already immense flash of a dying supermassive star. It's as if the star's final death cry has a melody, a strange, orderly pulse hidden within the ultimate act of cosmic chaos. The discovery of these pulsations was not immediate. It required patient, detailed analysis of supernova light curves, the graphs that plot a star's brightness over time as it explodes and fades. Normally, a core collapse supernova shows a characteristic sharp rise to peak brightness, followed by a long, gradual decline as radioactive elements decay and the expanding debris cloud thins out. But in a handful of these events, like the intriguing supernova 2015 BH, the smooth curve is defaced by a series of small but distinct wiggles. The brightness doesn't just fall, it oscillates, rising and falling again and again with a surprisingly regular period, sometimes repeating every few hours or days for weeks on end. This isn't random noise or instrumental error. It's a coherent signal, a real physical process imprinted on the light of the explosion itself. Detecting this signal is like finding a structured heartbeat in the middle of an earthquake, a clear message from the inaccessible heart of the cataclysm. So what cosmic mechanism could possibly create such rhythmic order from such unimaginable disorder? One of the most compelling theories points directly to the newborn object left behind in the wreckage, a neutron star. If the core collapse doesn't form a black hole, but instead a rapidly spinning, highly magnetized neutron star, a protomagnetar, this object could be the conductor of this explosive orchestra. This nascent neutron star would be pulsating violently, ringing like a bell struck by the collapse. These oscillations, known as non-radial pulsations, cause the entire star's surface to rhythmically expand and contract in complex patterns. As it pulsates, its powerful magnetic field is whipped around, and this motion can convert rotational energy into a pulsating wind of particles and radiation. This wind then slams into the expanding supernova debris shell from the inside, periodically heating it and causing the entire supernova to brighten in a regular, repeating pattern. In this model, the quasi-periodic pulsations are the literal heartbeat of a newborn stellar corpse, its first tremors broadcast to the universe through the glowing shroud of its own creation. But a newborn neutron star isn't the only potential metronome. Another fascinating possibility involves the sheer complexity of the explosion mechanism itself. Modern computer simulations suggest that the core bounce that triggers a supernova isn't always a clean, spherical blast. Instead, it can be a sloshing, chaotic process where enormous plumes of hot neutrinos rise from the core while cooler material falls back, creating a turbulent, standing wave pattern in the heart of the inferno. This sloshing effect could act like a piston, rhythmically modulating the energy output that is injected into the surrounding stellar envelope. The result would be a supernova that explodes in pulses, with the observed brightness flickering in time with these internal convulsions. It would be the explosion equivalent of a pot of boiling water, where large bubbles rise to the surface at semi-regular intervals, each one releasing a new burst of energy into the overlying material. This theory suggests the pulsations are a fossil imprint of the hydrodynamical instability that actually drove the explosion, a direct window into the turbulent birth of the blast wave. The profound importance of these flickers lies in the diagnostic power they grant us. A normal supernova is a brilliant but opaque fireball. We see the surface of the expanding debris, but the central engine is completely hidden from view. Quasi-periodic pulsations change that. They act as a form of cosmic seismology, allowing us to probe the otherwise invisible conditions at the very center of the explosion. By carefully measuring the period and amplitude of the pulsations, astronomers can essentially weigh the object causing them. A shorter period suggests a smaller, denser neutron star, while a longer period might point to a different mechanism or a slightly less compact object. It's a remote sensing technique for stellar corpses, giving us a way to distinguish between a supernova that created a neutron star and one that created a black hole, and even to estimate the strength of the magnetic fields involved. Each rhythmic flicker is a coded message, a data stream from the epicenter of stellar death that helps us unravel the final moments of a giant's life and the first moments of its remnant's existence. This strange musical behavior transforms a supernova from a mere spectacle into a sophisticated cosmic laboratory. And just when we thought we understood the limits of a star's final explosion, the cosmos unveils a class of supernova that makes even the brightest stellar death seem dim by comparison, the superluminous supernova. These are not merely bright explosions, they are cosmic holocausts of such staggering intensity that they can outshine entire galaxies, radiating with the energy of 10 to 100 normal supernova combined. Discovering one of these events is like finding a single lighthouse that outshines every other light in a massive country, and their existence forces us to confront a fundamental question. What conceivable engine could possibly power a stellar explosion to such insane levels of brilliance? To find the environments that breed these monstrous explosions, we must look back in time toward the early universe and its modern-day analogues, dwarf galaxies that are metal-poor. The term metal-poor in astronomy doesn't refer to a lack of iron or gold, but to a scarcity of all elements heavier than hydrogen and helium. These pristine cosmic backwaters are the closest thing we have to the conditions of the primordial cosmos, and they are the perfect cradle for supermassive stars that live fast, die young, and explode with unprecedented violence. In a metal-rich environment like our own Milky Way, a massive star's powerful winds, driven by heavy elements that absorb light efficiently, steadily strip away its outer layers long before its death, limiting its final mass and the power of its supernova. But in a metal-poor dwarf galaxy, a star's winds are much weaker. This allows it to hold onto its colossal bulk right up to the very end, retaining a tremendous reservoir of hydrogen, or if it's a Wolf-Rayet star, an enormous core of helium and heavier elements. When a star this massive and pristine finally collapses, it doesn't just fizzle. It detonates with a ferocity that its metal-rich cousins can scarcely imagine. So, what is the powerhouse behind this phenomenal flash of light? Astronomers have two primary suspects, and both are tied to the extreme behaviors of the supermassive stars we've been exploring. The first theory involves a process we've already encountered: the violent interaction of the supernova blast wave with dense material that the star ejected in its tumultuous final millennia. Imagine a star that has undergone multiple pulsational pair-instability eruptions, casting off shells of gas weighing many solar masses in the centuries before its final collapse. When the star's core finally gives way and the true supernova blast wave erupts outward, it doesn't expand into empty space. Instead, it smashes at incredible speed into these massive, slow-moving shells of its own former flesh. This collision is far more than a simple impact. It converts the enormous kinetic energy of the blast wave into intense thermal energy and light. The debris is heated to extreme temperatures, causing it to glow with a ferocious brightness that can persist for months, far outshining the radioactive decay of nickel-56 that powers a normal supernova. In this model, the superluminous event is essentially a supernova continually re-brightened by its own past, a spectacularly violent reunion of a star's present explosion with the ghosts of its earlier outbursts. The second leading theory posits an even more exotic central engine, a newborn magnetar. Recall that when a massive, rapidly spinning core collapses, it can form a neutron star with a magnetic field of almost incomprehensible strength, spinning hundreds of times per second. This object is a battery of unbelievable power. As this protomagnetar slows down, it sheds its rotational energy at an astronomical rate, emitting a relentless wind of particles and radiation. If this energetic output is efficiently absorbed by the expanding supernova debris surrounding it, that energy is converted into heat and light, supercharging the explosion's luminosity. This is like throwing a live high-power electrical cable into a cloud of gas. The entire cloud would light up brilliantly. For this to create a superluminous supernova, the magnetar must be spinning at its absolute limit, and its energy must be effectively trapped by the debris for a long period. This creates a sustained, brilliant glow that can account for the incredible peak brightness and the unusually slow fade of these events, outshining any conventional supernova by orders of magnitude. It is a stellar explosion powered not just by a single blast, but by the persistent, radiant spin-down of one of the universe's most powerful magnets. Determining which of these engines is at work, or if both can be, requires astronomers to play the role of cosmic detectives, scrutinizing the light curves and spectra of these brilliant events for telltale clues. A supernova powered by circumstellar interaction will often show distinct hydrogen lines in its spectrum, evidence that the blast wave is plowing through the star's own ejected hydrogen-rich envelope. Its light curve might also show a distinct, sustained plateau or even a second peak as it interacts with different shells of material. In contrast, a magnetar-powered supernova might lack hydrogen lines entirely if the star had already shed its outer layers, and its light curve may decline in a smooth, predictable way that matches the theoretical energy output of a spinning-down neutron star. The most extreme superluminous supernova ever recorded, such as SN 2007b, displayed characteristics that pointed strongly toward a pair-instability explosion, a single, colossal blast that completely obliterates the star. However, other events fit the magnetar model perfectly. This tells us that the title superluminous supernova is not a description of a single phenomenon, but a broad category of ultimate stellar deaths, each powered by its own unique catastrophic engine. These brilliant beacons are the universe's way of showing us that the final word in stellar evolution is not a single note, but a complex chord played on instruments of unimaginable power. After exploring the explosive finales of the universe's most massive stars, it might seem like stellar evolution follows a strict and predictable script. But in the crowded downtown districts of our galaxy, the ancient globular clusters astronomers have found stars that are flagrantly breaking the rules. These are the blue stragglers, massive, hot, and brilliantly blue stars that shine conspicuously amongst a population of ancient, cool, red stars. Their very existence is a cosmic paradox, like finding a group of vibrant teenagers at a retirement home party, and their presence forces us to rewrite the narrative of how stars can live and evolve. To appreciate just how bizarre a blue straggler is, you first have to understand the environment it calls home. Globular clusters are immense, spherical swarms of hundreds of thousands of stars, all bound together by gravity. Crucially, the stars within a single cluster are all believed to have been born at roughly the same time, over 10 billion years ago. Since then, stellar evolution has run its course. The most massive stars from that initial burst of star formation lived fast and died long ago in spectacular supernova. What remains are the long-lived lower mass stars, which have aged into cool red giants and dwarfs. According to our standard models, there should be no hot, blue, massive stars left in these ancient cities. They should have all burned out eons ago. Yet, when we point our telescopes at clusters like Messier 3 or Messier 30, we see them there anyway, brilliant blue points of light that look utterly out of place, shining with an energy that defies their advanced age. So how does a star manage to cheat cosmic senescence? How does it turn back the clock and appear young again? Astronomers have uncovered two primary and equally dramatic pathways for creating a blue straggler, both rooted in the uniquely crowded conditions of a globular cluster. The first is a scenario of stellar violence and merger, a direct result of the incredible density in a cluster's core. In these regions, stars aren't the distant, solitary points of light we see from Earth. They are packed together so tightly that their average separation can be smaller than the distance between our Sun and Pluto. In this celestial mosh pit, close encounters and direct collisions are not just possible, they are inevitable over billions of years. When two lower mass, older stars slam into each other, their cores and atmospheres can merge, combining into a single new star. This newly formed object has a larger mass and a fresh supply of hydrogen fuel dumped into its core, effectively reset its evolutionary clock. It becomes hotter, bluer, and more luminous than either of its progenitors, strutting onto the scene as a massive blue straggler that looks billions of years younger than its true chronological age. The second pathway is a slower, more intimate form of stellar vampirism that occurs in binary star systems. Imagine two stars orbiting one another, a common arrangement in the universe. One star ages slightly faster than its companion, evolving into a puffed-up red giant. As it expands, its outer layers become loosely bound by gravity, and if the stars are close enough, the stronger gravity of the smaller, denser companion star can begin to siphon this material away. This process, known as mass transfer, funnels fresh hydrogen fuel from the donor star onto the recipient. The recipient star, now gorged on this new hydrogen, becomes more massive. Its core, now supporting a heavier star, must burn hotter and faster to maintain equilibrium. This increased mass and reignited fusion cause the star to bloat with new energy, heating up its outer layers and transforming it from a cool, elderly star back into a hot, blue, and apparently youthful blue straggler. In this scenario, one star effectively rejuvenates itself by cannibalizing its partner, a cosmic case of stealing another's vitality to prolong its own brilliant prime. The evidence for these formation mechanisms is not just theoretical, it's written in the stars themselves. By analyzing the light from blue stragglers, astronomers can detect the chemical fingerprints of these violent histories. Stars that form through collisions often show atmospheres that have been thoroughly mixed, churned up from the inside out during the violent merger process. In contrast, stars that gain their mass through binary transfer can reveal a different signature. Their outer layers might show contamination from the processed material that was dredged up from the deep interior of their donor star. Furthermore, careful observations have actually caught binary blue stragglers in the act, with some systems showing clear signs of a companion, sometimes even a stripped-down stellar corpse like a white dwarf, which is the remnant of the donor star after it was bled dry of its outer layers. The existence of blue stragglers profoundly impacts our understanding of stellar populations and the dynamic life within star clusters. They are living proof that stars are not always isolated islands, but can interact, collide, and merge, fundamentally altering their destinies. These stellar anomalies are not mere curiosities. They are crucial tools for testing our models of stellar dynamics and evolution in dense environments. By studying them, we learn that a star's life story can be far more complex and eventful than a simple, solitary journey from birth to death. In the crowded heart of an ancient cluster, stars can find a fountain of youth, either through a catastrophic union or a slow, parasitic feast, ensuring that even in the oldest corners of our galaxy, brilliant blue light continues to shine against the odds. But what if a star, in its final death throes, didn't just leave a dense corpse nearby, but instead swallowed that corpse whole, creating a single, freakish celestial entity? This brings us to one of the most bizarre and theoretical concepts in all of astrophysics, the Thorne-Zitkow object, named after the physicists Kip Thorne and Anna Zitkow, who first proposed its existence in 1977. This hypothetical star is the universe's ultimate Russian nesting doll. Picture a vast, bloated red supergiant, so enormous that it could engulf the orbit of Jupiter. Now, imagine that buried deep within its fiery heart, where hydrogen fusion should be taking place, there isn't a stellar core at all, but a fully formed neutron star. This isn't a binary system, it is a single hybrid star, a cosmic chimera where the remains of one dead star power the violent and unnatural life of another. The formation of such a profoundly strange object requires a very specific and dramatic sequence of events, all centered on the chaotic dynamics of a dense star cluster or a tight binary system. The story begins with two massive stars born in a tight gravitational embrace. The more massive of the two evolves faster, burning through its fuel in a few million years before exploding in a supernova. In many cases, such a violent explosion would simply blast the binary pair apart, sending both stars flying separately through the galaxy. But if the supernova is slightly asymmetric, a kick that isn't quite strong enough to break the gravitational bond, the result is different. The collapsing core becomes a neutron star, and this ultra-dense remnant remains in orbit around its surviving, still living companion star. Now the stage is set for the main act. Over millions of years, the companion star itself begins to age, swelling inexorably into a red supergiant. As it expands, its outer atmosphere grows so vast that it eventually envelops its entire orbit, swallowing the neutron star companion whole. The neutron star doesn't just sit passively in the center. It spirals inward, dragged down by friction against the dense gas of the supergiant's envelope, eventually settling at the very center to become the new, utterly unnatural core of the giant star. The internal environment of a Thorne-Zitkow object would be unlike anything else in the known universe. In a normal red supergiant, the incredible heat and pressure at the core sustain a frenzy of hydrogen fusion, creating helium and releasing the energy that keeps the star from collapsing. But here, the core is a city-sized ball of neutrons, a billion times denser than any ordinary stellar material, and it's blazingly hot from its violent birth. This neutron heart doesn't fuse elements itself. Instead, it acts as a stupendous furnace, heating the surrounding gas of the supergiant's envelope from the inside out through sheer thermal contact. This intense external heating triggers a completely different mode of nucleosynthesis. The normal fusion processes are circumvented. Instead, a complex web of nuclear reactions, known as the slow neutron capture process or the S process, goes into overdrive. In this environment, atomic nuclei are bombarded by a flood of free neutrons, steadily building up heavier and heavier elements like rubidium, strontium, yttrium, zirconium, and even radioactive technetium that are then carried to the star's surface by massive convection currents. The chemical factory inside a Thorne-Zitkow object would produce a unique and exotic blend of elements, a radioactive signature that would make it stand out starkly from any ordinary star. For decades, this remained a fascinating but purely theoretical idea. How do you find a stellar Russian doll when it looks from the outside very much like a regular red supergiant? The key is in that unique chemical fingerprint. Astronomers hunt for these objects by taking detailed spectra of red supergiants, looking for stars that show extreme overabundances of those S-process elements like rubidium, lithium, and molybdenum, while simultaneously showing low levels of carbon and oxygen. In 2014, a team of astronomers announced they had found a strong candidate, a red supergiant in the Small Magellanic Cloud known as HV 2112. Its atmosphere was found to be loaded with lithium, rubidium, and other heavy elements in precisely the ratios predicted for the exotic interior of a Thorne-Zitkow object. The discovery sent waves of excitement through the astrophysics community, suggesting that after nearly 40 years, this theoretical oddity might have been found. However, the case isn't entirely closed. Subsequent studies have proposed alternative explanations for HV 2112's strange chemistry, suggesting it could be the result of an unusual but more standard bout of nucleosynthesis in a super-asymptotic giant branch star. The scientific debate continues, and the hunt for more candidates is ongoing, a testament to the challenge of confirming the existence of an object that so perfectly disguises its profound internal strangeness behind the placid facade of a familiar red giant. The search for the Thorne-Zitkow object is a brilliant example of theoretical physics providing a specific, testable prediction, pushing our observational capabilities to their limits in the quest to find the most deeply hidden secrets of the stellar world. Yet even amidst the brilliant fireworks of superluminous supernova and the clockwork precision of pulsations, there exists a theoretical fate for supermassive stars that is perhaps the most anticlimactic of all, a death not with a bang but with a sputter. This is the strange destiny of the silicon fizzler, a star that fails so catastrophically in its final moments that it cannot even muster the energy for a proper explosion. Imagine a stellar titan reaching the very last stage of its life, its core layered like a cosmic onion with successive shells of hydrogen, helium, carbon, neon, oxygen, and finally silicon. In a standard core collapse supernova, this silicon would fuse over a period of about a day into iron, the final element that can be fused while releasing energy. The formation of that iron core is the trigger for the final collapse and the subsequent spectacular rebound explosion. But for a fizzler, that final act never arrives. The orderly procession of nuclear fusion breaks down in a frenzy of its own making, leading to a disruption so total that the star is utterly torn apart without the signature flash of a supernova. The key to this failure lies in the physics of silicon burning itself. This is the last desperate energy-generating process available to a massive star, and it is incredibly sensitive to temperature. For the most massive stars, those pushing the upper limits of what is theoretically possible, the core can become so hot and dense that silicon fusion doesn't proceed in a controlled, stable manner. Instead, it ignites with a ferocious, runaway intensity. The core becomes a maelstrom of superheated gas, with convection currents so violent and rapid that they effectively churn the entire core region. This extreme convection has a devastating consequence. It mixes the freshly synthesized iron group elements, the ash of silicon burning, back into the still fusing silicon fuel. This is a cosmic catastrophe. In a normal star, the iron ash would sink to the center, gradually building the inert core that will eventually collapse. But here, the convective currents are so powerful they prevent this separation. The iron is constantly stirred back into the furnace where it acts as a poison. Fusing iron requires energy, it doesn't release it. So, as more and more iron is mixed into the fusing silicon, it begins to sap the core's energy output, cooling it from within at the very moment it needs to be hottest. This internal sabotage leads to a rapid and total loss of pressure support. The core, which was being held up by the tremendous energy released from silicon fusion, suddenly finds its power source failing. The inward pull of gravity, which has been held at bay for millions of years, becomes instantly and completely dominant. But this is not the coherent, structured collapse that leads to a core bounce and a shock wave. This is a chaotic, global implosion of the entire stellar core. Without a sharp density boundary between an iron core and the surrounding silicon shell, the collapse happens throughout a large region of the star's interior. The result is not a focused rebound, but a complete and total disruption. The infalling material from the outer core and the overlying stellar envelope meets no hard surface to bounce from. Instead of a supernova, the star undergoes a massive deconstruction. It is ripped apart from the inside out, its material falling inward only to be dispersed in a violent, disorganized eruption. It's a fizzle in name only, as the energy released is still colossal, but it lacks the coherent, energetic signature of a true supernova. The star is dismantled, its remains scattered into a cloud of hot gas that will rapidly expand and fade, leaving behind no compact remnant, no neutron star or black hole, because the entire core was disrupted in the process. Observing such an event would present a profound challenge to astronomers. A silicon fizzler would not produce the characteristic bright, long-lasting light curve of a supernova powered by nickel-56 decay. There would be no brilliant flash to catch the attention of automated sky surveys. Instead, it might manifest as a sudden, brief, and peculiar ultraviolet or X-ray transient, a quick burp of energy as the star's internal structure disintegrates, followed by a relatively rapid fade. It might be mistaken for a peculiar, low-energy supernova or an unusually violent stellar outburst. Confirming the existence of fizzlers relies heavily on sophisticated computer simulations that model the intricate hydrodynamics and nuclear physics in these extreme environments. These models have to account for the complex interplay between turbulent convection, nuclear reaction rates, and the behavior of matter at densities and temperatures far beyond what we can replicate on Earth. When scientists run these simulations for the most massive stellar progenitors, the fizzler outcome emerges as a distinct possibility for stars in a specific mass range, providing a theoretical pathway for a star to vanish without the traditional fanfare. The implications of this fizzling mechanism are profound, as it suggests there could be an entire population of supermassive stars that end their lives in this dark, unceremonious way. These failed explosions would be cosmic ghosts, leaving no dense corpse to mark their grave and producing a very different chemical legacy. A standard supernova is a primary source for seeding the galaxy with heavy elements like oxygen, magnesium, and silicon itself. A fizzler, by disrupting the star so completely, might still distribute these elements, but it would fail to produce the heavier elements like gold and uranium that are forged in the extreme conditions of the supernova explosion itself or in the merger of neutron stars. The existence of fizzlers could therefore help explain certain chemical abundances in the universe, acting as a counterbalance to the productive chemical factories of successful supernova. This strange, quiet death represents a fundamental limit to stellar stability, a point at which the star's own internal engine becomes so inefficient that it simply shuts down, demonstrating that even for the largest stars, the final step toward iron can be a bridge too far, resulting not in a glorious finale, but in a final, chaotic, and ultimately silent unraveling. Now we arrive at a cosmic detective story, a genuine puzzle that has astronomers scratching their heads. It's known as the red supergiant problem, and it strikes at the very heart of our ability to predict stellar deaths. The problem is straightforward, yet deeply perplexing. When we look at archival images of galaxies taken before a supernova occurs, we can often identify the star that blew up. For core collapse supernova, the progenitors are typically red supergiants, those vast, cool, inflated stars in their final evolutionary stage. The theory is beautifully clear. The more massive a star is at birth, the more massive its red supergiant phase should be, and the brighter its supernova will be. But the observations tell a different, more confusing story. We have found plenty of supernova progenitors with initial masses up to about 18 times the mass of our Sun. Yet for stars born heavier than that, the true supermassive stars of 20, 30, or even 40 solar masses, the pre-explosion images show a glaring emptiness. Where are they? It's as if the universe's most massive stars are vanishing from the stage before the final curtain call, dying in secret and leaving behind only a mystery. One of the most compelling solutions to this enigma is as dramatic as it is dark: the direct collapse. Imagine a red supergiant so immensely massive that its core, once it finishes fusing silicon into iron, has no fight left to give. In a typical supernova, the core collapse rebounds, creating a shock wave that tears the star apart in a brilliant explosion. But for these heavyweight champions, the core may be so gravitationally powerful that when it collapses, the resulting black hole forms almost instantaneously. The shockwave generated by the core bounce simply doesn't have the energy to overcome the tremendous gravitational pull of the newborn black hole. Instead of racing outward and blasting the star's envelope into space, the shockwave stalls and is effectively swallowed whole. The entire stellar envelope, a vast cloud of hydrogen and helium weighing many solar masses, simply falls inward down the gravitational well into the waiting black hole. From the outside, you wouldn't see a brilliant supernova. You might witness a brief, faint optical flare as the outer layers are cut off from their energy source and a small amount of material is ejected, but it would be a pitifully dim event compared to a full-fledged supernova. The star would then simply wink out. It disappears from the visible universe, leaving behind a silent, dark tomb. This unseen death could easily explain why our pre-supernova images are empty for the most massive stars. Their final moments are not a blaze of glory, but a swift and final descent into darkness. But there is another, more transformative possibility. Perhaps these supermassive stars don't die secretly because they are hiding their deaths, but because they are hiding their true identities. This explanation focuses on the extraordinary mass loss that characterizes the most massive stars throughout their lives. We've already seen how hypergiants and luminous blue variables can shed entire solar masses in violent outbursts. Now apply that process on an even grander scale. A star born with 30 times the mass of the Sun might, through a combination of relentless stellar winds and periodic giant eruptions, shed more than half of its initial mass by the time it reaches the red supergiant phase. It effectively diets itself down, transforming from a true heavyweight into a middleweight contender. By the time its core is ready to collapse, it may only have 10 or 15 solar masses left in its envelope. When it finally explodes, it does so as a star that appears from the outside to have been born with a much lower mass. So when astronomers look at the pre-explosion images, they see the star in its final, whittled-down state. They correctly identify a red supergiant of, say, 15 solar masses as the progenitor, and the supernova that follows matches that expectation perfectly. The star's true, more massive birth identity is erased by its own self-destructive weight loss, solving the red supergiant problem not through a dark collapse, but through a cosmic case of mistaken identity. The ongoing search for evidence to support these theories is pushing observational astronomy to its limits. The direct collapse scenario predicts the existence of these faint optical transients. In recent years, surveys have begun to catch a handful of these curious events supernova that are inexplicably dim and short-lived. One of the most famous examples is supernova 2008 Ha, which was 100 times fainter than a typical core collapse supernova. Its faintness and its chemical signature were both consistent with a massive star whose outer layers largely failed to be ejected, pointing strongly toward a partial collapse scenario. On the other side, detailed studies of the environments around supernova are providing clues about mass loss. By analyzing the material surrounding the explosion, astronomers can piece together the history of the star's final centuries. If they find evidence of dense, complex shells of gas that the star ejected shortly before dying, it supports the idea that the progenitor was actively and violently shedding its mass, disguising its true initial heft. Each strangely dim supernova and each complex circumstellar environment acts as another piece of evidence in this cosmic court case, helping us determine the final fates of the universe's largest stars. The red supergiant problem is no longer just a frustrating gap in our knowledge. It has become a fertile ground for discovery, forcing us to refine our models and acknowledge that the death of a star can be a far more nuanced and clandestine affair than we ever imagined. While we can piece together the lives of stars from their final, brilliant explosions, what if we had a way to literally look into the past and observe their historic tantrums directly? This brings us to one of the most poetic and powerful phenomena in observational astronomy: light echoes. Imagine the night sky not as a static picture, but as a place where light is still traveling, carrying messages from long ago. When a supermassive star like Eta Carinae unleashed its great eruption in the 1840s, the initial flash of light reached Earth and was witnessed by astronomers of that era. But that was only the direct beam. The full story was still unfolding across the light years, traveling not just toward us, but in every direction. Some of that light raced past our planet and continued onward into the darkness until it eventually encountered vast, faint clouds of interstellar dust floating in the depths of space. These dust clouds act like a colossal cosmic projection screen. When the light from the historic eruption finally slams into these distant dust sheets, it is scattered and reflected, and a small fraction of that reflected light is sent on a new, longer path back toward Earth. We see this as a luminous ring or an arc expanding outward from the long quiet star, a ghostly replay of an event that human eyes saw over a century prior. It is a literal echo, not of sound, but of light itself, allowing us to witness the same stellar outburst multiple times across the generations. The true magic of a light echo, however, isn't just in the pretty picture, it's in the scientific treasure trove it represents. This reflected light is not just a simple glow, it carries with it the full spectroscopic signature of the original eruption. When we train our modern, powerful telescopes, like the Hubble Space Telescope or large ground-based spectrographs, on a light echo, we are not looking at the star as it is today. We are capturing the actual light that left the star during its violent event centuries ago. We can run that ancient light through a prism, break it into its constituent colors, and analyze its spectrum just as if we had a time machine pointed directly at Eta Carinae in the year 1843. This allows us to perform forensic astronomy on an event that predates modern astrophysics. We can determine the temperature of the ejected material, its chemical composition, its density, and the velocity at which it was blasted into space. It's like finding a perfectly preserved recording of a famous speech from history, but with the added ability to analyze the speaker's breath for chemical traces, giving us insights that the original audience could never have dreamed of. This time-traveling capability has profoundly reshaped our understanding of specific historic outbursts. Take the case of P Cygni, a star that underwent a dramatic eruption in the 17th century, brightening enough to be seen with the naked eye before fading away. For centuries, its exact nature was debated. Was it a true supernova imposter? What exactly was ejected? By studying the light echoes from P Cygni's event, astronomers were able to conclusively determine that it was a massive ejection of a hydrogen-rich shell, similar to the great eruption of Eta Carinae but on a slightly smaller scale. The spectroscopy revealed powerful stellar winds and the specific conditions in the material that was flung into space, confirming it as a key example of a luminous blue variable in eruption. Without the light echo, this would just be an interesting historical footnote. With it, we have a detailed physical dataset. Similarly, light echoes from supernova, like the one from Tycho Brahe's famous supernova of 1572, have allowed us to classify it definitively as a Type Ia explosion, settling a centuries-old debate about its nature by analyzing light that is only now, hundreds of years later, completing its long, indirect journey to our telescopes. The practical observation of these echoes is a race against time and geometry. The reflected light takes a longer path to reach us than the direct light did, creating a delay that can be decades or even centuries. Because the dust cloud is often a complex, three-dimensional structure at a specific distance from the star, the echo manifests as an expanding ring. This isn't because the light is moving outward through the dust, it's a simple effect of geometry. Think of it like the wake of a stone thrown into a pond but illuminated from within. As time passes, light from later phases of the eruption reaches increasingly distant parts of the dust cloud, causing the ring to appear to grow larger in the sky over a period of years. Astronomers have to be patient and persistent, monitoring these systems for years to capture the full evolution of the echo. Each new ring that appears is like turning a page in a history book, revealing a later chapter in the eruption story. This patient work transforms these faint, ghostly rings from mere curiosities into one of the most powerful tools in an astronomer's kit. A direct link to the past that allows us to apply our 21st century technology to the great stellar mysteries of previous centuries, ensuring that the light of long-dead stars continues to teach us new lessons about the lives of the cosmos's most magnificent giants. After exploring the echoes of ancient stellar cataclysms, we now turn our gaze to a completely different kind of cosmic object. One so peculiar and small it was actually discovered by citizen scientists. These are the green P galaxies, and despite their unassuming, almost cute name, they hold within them the roaring, violent legacy of supermassive stars, acting as a living window into the universe's most formative and turbulent era. To understand this profound connection, we must first picture what a green P galaxy actually is. Imagine a galaxy not like our grand, stately Milky Way with its hundreds of billions of stars, but a tiny, chaotic dwarf. A green P is incredibly compact, often less than 5% the size of our galaxy, and yet it is a maelstrom of creation. Within its small volume, stars are being born at a ferocious, almost unsustainable rate. If our Milky Way formed stars at an equivalent density, it would be producing thousands of new stars every year instead of the one or two it manages. This frantic starbirth gives these galaxies their distinctive greenish hue in astronomical images. That color isn't from green stars, which don't exist, but from an intense, overwhelming glow of doubly ionized oxygen, a telltale signature of gas that has been blasted by an enormous amount of high-energy ultraviolet radiation. And that is precisely where the supermassive stars enter the story. You see, that specific kind of ultraviolet radiation doesn't come from calm, long-lived stars like our Sun. It is the exclusive signature of the hottest, most massive, and shortest-lived stars in the cosmos, the very Wolf-Rayet stars, luminous blue variables, and O-type giants we've been discussing. A green P galaxy isn't just forming a lot of stars, it is forming a staggering, top-heavy population of stellar titans. In these cramped cosmic nurseries, supermassive stars are not rare anomalies, they are the dominant population. Their collective fury is what defines the entire galaxy. The relentless stellar winds from thousands of Wolf-Rayet stars slam into each other, and the surrounding gas, creating vast pressurized bubbles and shockwaves that trigger even more star formation. The intense radiation from countless blue hypergiants strips electrons from atoms, ionizing the galaxy's entire reservoir of gas. The galaxy itself becomes a single, glowing nebula, illuminated from within by the combined might of its most massive and violent inhabitants. A green P is, in essence, a galaxy-wide H-Roman II region, a stellar engine whose roar is powered almost entirely by the brief, brilliant lives of supermassive stars. This incredible local phenomenon provides us with our most crucial analog for understanding one of the most important transitions in cosmic history, the epoch of reionization. In the very early universe, after the Big Bang cooled enough to form neutral hydrogen atoms, the cosmos entered a period known as the Cosmic Dark Ages. The universe was an opaque fog of neutral gas, and light could not travel freely through it. Something had to happen to clear this fog and make the universe transparent, and that something was reionization. Astronomers have long theorized that the first stars and galaxies, which formed from pristine hydrogen and helium, were likely dominated by supermassive stars far larger than any we see today. When these first-generation giants, known as population Roman III stars, were born, they would have lived and died in much the same violent way as the stars in green P galaxies. Their intense ultraviolet radiation would have acted like a cosmic ultraviolet lamp, slowly burning away the neutral hydrogen fog by splitting those atoms back into protons and electrons, a process called ionization. Green P galaxies are the only objects we have found in the nearby universe that replicate the conditions needed to drive such a large-scale transformation. By studying them up close, we can test our models of how starlight can reshape an entire universe. We can measure exactly how much ionizing radiation escapes from such a compact, star-bursting environment. In most modern galaxies like our own, much of the harsh ultraviolet light from massive stars is absorbed by local dust and gas before it can escape into intergalactic space. But in the leaky, turbulent confines of a green P galaxy, observations show that a significant fraction of this transformative radiation, sometimes up to 10 or 20%, actually punches through and streams out into the void. This escape fraction is the critical number that determines a galaxy's power to contribute to reionization, and green peas demonstrate that it is not only possible but highly efficient under the right conditions. They are proof of concept laboratories, showing that galaxies dominated by supermassive stars are more than capable of performing the universe-altering task of reionization. The legacy of these small green powerhouses doesn't end with their light. The violent deaths of their supermassive stars are just as important. The frequent supernova and gamma-ray bursts within a green pea galaxy do more than just create black holes and neutron stars. They act as enormous feedback engines. These explosions eject newly forged heavy elements, the carbon, oxygen, iron, and silicon created in stellar cores and supernova blasts at tremendous speeds, polluting the galaxy's gas and flinging it far out into the circumgalactic medium. This process, called chemical enrichment, is what seeds the universe with the raw materials for planets and, ultimately, life. A green pea galaxy is therefore a microcosm of the entire cosmic cycle of birth, death, and rebirth. It showcases how the most extreme stellar behaviors, from the relentless winds of living titans to the cataclysmic explosions of their deaths, don't just shape their immediate surroundings but can dictate the evolutionary path of an entire galaxy and contribute to the chemical and physical evolution of the cosmos on the largest scales. In these small, green, and frenzied islands of stars, we see a scaled-down replay of the forces that lit up the dark, early universe and forged the elements that make our own existence possible. But what happens when a star's very spin becomes its defining feature, a force so potent it can reshape the star's body, extend its life, and ultimately script one of the most violent deaths in the cosmos? This brings us to the pivotal role of rapid rotation, a behavior where a star doesn't just spin, it whirls on the very edge of self-destruction. Imagine a stellar titan so massive that its equatorial surface is flung outward by centrifugal force, battling against the inward pull of its own gravity. The result is not a perfect sphere, but a squashed oblate spheroid, like a cosmic pumpkin or a beach ball someone is sitting on. This dramatic bulging at the equator and flattening at the poles is more than just a curiosity. It's the outward sign of an internal revolution that changes everything about how the star lives and dies. The most profound consequence of this near breakneck spin is a phenomenon known as rotational mixing. In a slow-spinning star like our Sun, the interior is highly stratified, with distinct layers of different elements resting one atop the other like those in a cosmic onion. The heavy elements forged in the core generally stay there, while the hydrogen fuel in the outer layers remains separate. But in a rapidly rotating supermassive star, this orderly structure breaks down. The ferocious spin churns the star's interior, creating powerful currents and turbulence that stir the entire stellar pot. This mixing acts like a gigantic conveyor belt, continuously dragging fresh, unburned hydrogen from the outer envelope down into the searingly hot core. Simultaneously, it carries the helium ash produced by fusion away from the core and out toward the surface. This constant replenishment of fuel is like giving a fire a limitless supply of oxygen. It allows the star to burn brighter and for a significantly longer time than a non-rotating star of the same mass. This extended lifespan has a crucial side effect. By the time the star's core is ready to collapse, its outer layers are polluted with the byproducts of core fusion, like nitrogen and helium, giving it a unique chemical signature that astronomers can detect. This reservoir of spin, however, is not just about prolonging life. It's the key ingredient for an ultimate death of unparalleled violence. For a star to produce a long-duration gamma-ray burst, the universe's most powerful focused explosion, it needs two things: a massive core to form a black hole, and an enormous reserve of angular momentum to form an accretion disk around that newborn black hole. A rapidly rotating supermassive star is the perfect progenitor because it carries this incredible rotational energy right up to its final millisecond. When the core of such a star collapses, the conservation of angular momentum causes its spin to skyrocket. The infalling material doesn't plunge directly into the black hole. Instead, it swirls into a vast, incredibly hot and hyper-energetic accretion disk. This disk is the central engine of the gamma-ray burst, and the star's initial rapid rotation is what provides the raw power to launch the relativistic jets that can pierce through the stellar envelope and be seen across the universe. A slower spinning star of the same mass might produce a brilliant supernova, but it would lack the focused, jet-driven cataclysm of a gamma-ray burst. The spin is what makes the difference between a grand firework and a celestial cannon shot. Observing these rapidly rotating giants, however, presents a unique challenge. We can detect their high spin indirectly through their oblate shape, which affects the star's brightness and temperature at different latitudes, and through the chemical peculiarities in their spectra caused by that intense internal mixing. Stars like Gamma Cassiopeiae serve as nearby, slightly less massive examples, showing us the disks and outbursts associated with critical rotation. But to find the true progenitors of gamma-ray bursts, we look to metal-poor dwarf galaxies, where the absence of heavy elements results in weaker stellar winds. Since stellar winds carry away not just mass but also angular momentum, a star in a metal-poor environment can retain its ferocious spin throughout its life, perfectly preserving the rotational power needed for its final, spectacular act. This intricate dance between mass, spin, and environment underscores a fundamental truth. In the realm of supermassive stars, how a star moves can be just as important as how much it weighs, dictating a destiny that ranges from a prolonged, brilliant life to a death that unleashes a beam of energy capable of briefly outshining the rest of the cosmos combined. Now, let's shift our attention from the explosive deaths of these titans to a phase of strange, sculpted beauty in the life of some supermassive stars, a phase where they don't just shed material, but forge that material into exquisite, glowing disks that seem to defy the very physics that governs their creation. We are entering the enigmatic world of BE supergiants. The name itself is peculiar. The B denotes their spectral class hot, massive stars, much hotter and larger than our Sun. The lowercase e in brackets, however, is the critical clue. It stands for emission, and it signifies that the star's spectrum isn't just marked by the dark absorption lines we typically see, but is dominated by bright, shining lines emitted by specific elements in the star's surroundings. And these aren't just any elements. We're talking about ionized metals like singly ionized iron and titanium, which require very specific, dense environments to glow so prominently. But the mystery doesn't stop there. These stars also show a tremendous excess of infrared radiation, a clear sign that they are surrounded by vast quantities of warm, circumstellar dust. This combination, the emission lines and the infrared glow, points to a single, breathtaking conclusion. The star is enshrouded in a dense, orbiting disk of gas and dust, a celestial jewelry box of its own creation. What makes these disks so peculiar and so different from the blistering stellar winds of Wolf-Rayet stars is their nature. This isn't a fast, thin, spherical wind blowing off into space. Observations reveal this material is moving relatively slowly and is confined to a dense, non-spherical structure, most likely a disk or a torus circling the star's equator. It's as if the star isn't just exhaling its atmosphere, but is carefully spinning it out into a vast cosmic carousel. This structure has profound effects. The dense gas in the disk is what produces those brilliant emission lines, as it is constantly being bathed and excited by the star's intense ultraviolet light. Meanwhile, the dust grains, which can only form in the cooler, shielded regions far enough from the star's searing radiation, absorb its visible light and re-radiate it as the copious infrared glow that makes these objects so distinctive. This entire system, a hot, central supergiant encircled by a cooler, dusty disk, creates an object of stark contrasts, a celestial hybrid that is both a brilliant blue powerhouse and the center of a much more serene, structured nebula. The central puzzle, the great debate surrounding BE supergiants, is simply this. How does a star like this, with such a powerful radiation field, manage to form and maintain such a dense, organized disk? A star this massive should be blowing off its outer layers in a fierce, spherical wind. Gravity and radiation pressure should not allow for such a lopsided, concentrated structure to persist. One of the leading theories points the finger directly at the star's rotation. Imagine a supermassive star spinning so rapidly at its equator that centrifugal force becomes a major player, effectively reducing the local gravity and making it much easier for the star's radiation to push material away from its equatorial regions. This would create a preferential outflow right at the star's waistline, a focused, equatorially enhanced wind that could naturally pile up into the dense disk we observe. In this scenario, the star's own incredible spin acts as a potter's wheel, shaping its own expelled material into a structured, orbiting form. But there's another, equally compelling explanation that involves a cosmic dance partner, binary interaction. Many astronomers suspect that a significant number of BE supergiants are not single stars at all, but exist in a tight binary system with an unseen companion. The presence of a second star offers a beautifully elegant mechanism for disk formation. As the two stars orbit one another, the powerful gravitational pull of the companion can literally siphon material away from the primary supergiant, pulling it off not in a sphere but in a focused stream. This stream of stolen gas doesn't fall directly onto the companion. Instead, because of the orbital motion, it misses the star and settles into a vast, swirling accretion disk that encircles the entire binary system. This would be a circumbinary disk, a structure created not by the supergiant's winds, but by the complex gravitational ballet between two stellar titans. This theory elegantly explains the disk's density and its relatively slow Keplerian motion, as the material is following orderly orbital paths dictated by the system's combined gravity. The distinction between these two formation models is more than just academic. It has huge implications for the star's ultimate fate and its role as a cosmic chemist. A disk formed through rapid rotation suggests a star that is profoundly mixing its interior, potentially extending its life and altering the chemical composition of the material it ejects. In contrast, a disk formed through binary mass transfer is a testament to stellar interaction, a process that can dramatically alter the mass and spin of both stars involved, pre-programming them for a specific kind of supernova or even a gamma-ray burst. Furthermore, these dusty disks are phenomenal chemical laboratories. They provide the perfect sheltered environment for dust grains to coagulate, forming silicates and other complex minerals that would be instantly destroyed in the harsh environment of a spherical stellar wind. In this way, BE supergiants could be significant contributors to the cosmic dust budget, the very stuff that later forms planets and ultimately the building blocks of life. Their strange, forbidden disks are not just beautiful anomalies, they are active, dynamic factories, and whether they are born from a star's frantic spin or a gravitational tug of war, they stand as some of the most elegantly structured and mystifying objects in the stellar menagerie. Yet here we find one of the universe's most profound recycling programs, where the catastrophic death of a star becomes the essential genesis of new worlds. This is the supernova dust factory phenomenon, a process where the seemingly destructive force of a stellar explosion becomes a creative one, forging the very building blocks for future planets and ultimately life itself. For a long time, astronomers were puzzled by a cosmic contradiction. When they looked at the most distant, ancient galaxies, the ones we see as they were just a few 100 million years after the Big Bang, they found them to be absolutely filled with immense amounts of dust. This was a genuine mystery. The universe began with only the lightest elements, hydrogen, helium, and a trace of lithium. Everything else, the carbon in our bodies, the oxygen we breathe, the silicon in rocks, and the iron in our blood had to be forged inside stars. But how did the raw elements forged in stellar cores get transformed from isolated atoms floating in space into the tiny, solid dust grains that are so abundant in the early cosmos? The answer, we now know, lies in the turbulent, expanding aftermath of a supermassive star's final explosion. The journey from a cloud of hot gas to a speck of cosmic dust is a delicate one, requiring just the right conditions. In the immediate wake of a supernova, the environment is anything but hospitable to such fragile structures. The ejected material is a blazingly hot plasma, a soup of atomic nuclei and electrons racing outward at thousands of kilometers per second. In this inferno, any atoms that dare to link up and form molecules are instantly torn apart by the intense heat and radiation. But as the supernova remnant expands, it does two crucial things. It cools, and it sweeps up vast amounts of the cooler surrounding interstellar gas. Over a period of several years to a few decades, the temperature in the dense, shocked inner regions of the ejecta plummets from millions of degrees to just a few thousand, and then down to just a few hundred degrees. This cooling is the starting gun for a remarkable phase change. Once the temperature drops below about 2000 degrees Kelvin, atoms that were once solitary begin to find each other. Carbon atoms link up into chains and rings, and elements like silicon, magnesium, and oxygen start to bond, forming the seeds of more complex solids. Then the real magic begins, in a process that is astonishingly similar to soot forming in a candle flame or steam condensing into water droplets in our atmosphere. These molecular clusters act as nucleation sites. Atoms from the surrounding gas glom onto these tiny seeds, layer by layer, building them up into fully fledged dust grains. The specific composition of the dust depends entirely on the chemistry of the supernova ejecta. In the oxygen-rich zones of the explosion, we get grains of silicates, the essence of sand and rock, and alumina, the basis for sapphires and rubies. In pockets that are rich in carbon, we get tiny diamonds and, more commonly, graphite and amorphous carbon grains, the fundamental component of soot. These are not the large, precious gems you might imagine. They are nanoscopic, most smaller than a wavelength of light, but they are trillions upon trillions of them. A single supernova can, in a relatively short cosmic timescale, produce an amount of dust equivalent to the mass of our entire sun, flooding its local region of the galaxy with a fine, elemental mist. For decades, this was an elegant theory, but direct confirmation was elusive because the dust itself is so difficult to observe. It absorbs visible light, hiding the stars behind it, but it re-radiates that absorbed energy in the far infrared part of the spectrum. The breakthrough came with powerful infrared telescopes like the Spitzer Space Telescope and the Herschel Space Observatory, which could peer directly into these cosmic nurseries. One of the most stunning and well-studied laboratories for this process is the supernova remnant Cassiopeia A, the expanding debris cloud from a star that exploded around the year 1680. Observations have revealed CASSA to be absolutely teeming with freshly formed dust. Spectrometers have identified the specific infrared signatures of warm silicates, carbon, and alumina dust, all residing within the cool, dense clumps of ejected material. We are essentially watching this condensation process happen in real time, seeing the direct evidence that the violent death of a star just 300 years ago is already manufacturing the raw materials for a future planetary system. This dust factory phenomenon is not just a fascinating footnote, it is a cornerstone of cosmic ecology. These supernova-forged grains are the primary ingredient for the next generation of stars and planets. When a cloud of interstellar gas and dust collapses to form a new star, it is this dust that helps to cool the cloud, allowing it to fragment and condense more efficiently. The dust grains also provide surfaces for chemical reactions, allowing simple molecules like molecular hydrogen and water to form. Then, as the new star ignites, the dust in the surrounding disk begins to clump together, forming pebbles, then planetesimals, and eventually the cores of planets. Every rocky world like Earth and every grain of sand on its beaches contains material that was once part of this life cycle, forged in the heart of a long-dead supermassive star, condensed in the expanding shell of its supernova, and then incorporated into the cloud that gave birth to our solar system. The supernova dust factory transforms stellar death from a mere ending into a vital link in a grand, cosmic cycle of rebirth, proving that even in its most violent moments, the universe is tirelessly working to build the foundations for new worlds and new possibilities. But the death of a star is not always the final word in its cosmic story. For the stellar titans locked in a tight gravitational embrace, their shared demise sets the stage for a final, silent dance that sends tremors through the very fabric of the universe itself. These are the gravitational wave progenitors, binary systems of supermassive stars whose ultimate fate is not merely to explode, but to collapse into black holes and spiral together in a cataclysm that literally stretches and squeezes the continuum of space and time. The journey from a binary pair of luminous giants to a source of the most powerful ripples in spacetime is a perilous one, filled with potential pitfalls that can either forge the perfect engine for a gravitational wave signal or dismantle it entirely before the final act even begins. The ideal pathway begins with two massive stars born close together, their fates intertwined from the outset. They orbit each other in a cosmic waltz that might last only a few million years, a fleeting moment in cosmic terms. The first critical test comes as the more massive star exhausts its fuel and begins its death spiral. It swells into a vast red supergiant, and in such a tight binary system, this expansion is a moment of extreme danger. If the stars are too close, the outer layers of the swelling giant can envelop its companion, dragging it down into a stellar merger that obliterates the binary system entirely. This common envelope phase is a violent, messy process. The smaller star spirals inward within the bloated atmosphere of its partner, transferring orbital energy and angular momentum to the envelope, which is then ejected into space in a grand, swirling nebula. For the binary to survive this phase and proceed toward a future as gravitational wave source, this common envelope must be ejected with perfect precision. The process must strip the giant down to its bare helium core without causing the two stars to merge, leaving behind a tight pair, a helium star or a Wolf-Rayet star and its main sequence companion. This is a celestial high-wire act, and only a fraction of binaries successfully navigate it. Should the system survive, it then faces a second, equally dramatic challenge: mass transfer. As the second star in the pair begins its own evolution and expands, it can start to transfer its own mass onto its now compact companion, which may already be a black hole or a neutron star. This is a delicate balancing act. A stable, slow transfer of mass can tighten the binary's orbit, priming it for the final collapse. However, if the transfer is too rapid or unstable, it can once again lead to a merger, or it can dramatically alter the spin and mass of the receiving black hole, changing the ultimate properties of the final binary. The system must carefully manage this transfer of stellar material, all while both stars are buffeted by their own ferocious stellar winds, which steadily sap the system of mass and angular momentum. Every step of this long and turbulent evolution shapes the final properties of the two black holes that will eventually form, their masses and, crucially, their spins. A black hole's spin is a key fingerprint of its birth, determined by whether its progenitor star was rapidly rotating or was spun up by accreting material from its partner. This spin imprints itself directly onto the gravitational wave signal that the eventual merger will produce. If the binary can successfully weather all these storms, avoiding premature merger, ejecting its common envelopes, and managing stable mass transfer, it arrives at the final, breathtaking sequence. The second star finally exhausts its own fuel and undergoes its own core collapse, resulting in a second black hole. Now the stage is set. You have two black holes, the ultra-dense remnants of those once brilliant stars, locked in a mutual orbit. They are no longer shedding mass through winds or eruptions. Their evolution is now governed purely by the loss of energy to gravitational waves. As they circle each other, they constantly radiate tiny, imperceptible ripples in space-time. This slow, steady leakage of energy causes their orbits to decay over hundreds of millions of years. They draw closer and closer, their orbital speed increasing until, in the last few seconds, they are whipping around each other at a significant fraction of the speed of light. The emission of gravitational waves becomes a roar. Their dance becomes a final, desperate plunge, culminating in a violent merger that converts an amount of mass equivalent to several of our suns directly into pure energy in the form of a gravitational wave burst. This is the event that instruments like LIGO and Virgo have now detected, a fleeting signal that tells us of a union that occurred billions of years ago in a distant galaxy. The detection of these waves has opened an entirely new window onto the lives of supermassive stars, allowing us to perform a kind of cosmic archaeology. By analyzing the gravitational wave signal, the chirp that rises in frequency and amplitude, scientists can read the story of the progenitor binary. They can deduce the masses of the two black holes, which reveal the initial masses of the stars that formed them. They can even infer their spins, which provide clues about whether the stars were rapidly rotating from birth or were spun up by that complex mass transfer. Each merger event is a data point, a confirmation of a theoretical pathway that begins with two massive stars living and dying together. The existence of these binary black holes proves that the universe can, against all odds, successfully guide these turbulent stellar partnerships through a gauntlet of potential disasters to create the perfect conditions for a final, silent cataclysm that we can now, from across the cosmos, just barely hear. Now, let's shift our focus from the solitary deaths of stellar titans to the intricate and rhythmic dance of two giants locked in a gravitational embrace, a system that literally wears its heartbeat on its sleeve for the entire universe to see. We are entering the realm of eclipsing massive binaries, where the precise, clockwork observations from telescopes like Kepler and TESS have revealed not just simple eclipses, but a symphony of light that tells a profound story of gravity, tides, and stellar structure. When two massive stars orbit one another, their gravitational interplay creates a light curve, a graph of their combined brightness over time that is far more complex and revealing than a simple on and off blinking. It is a rich, dynamic signal, and for certain systems, this signal includes a distinct, repeating spike that looks for all the world like a cosmic electrocardiogram, a heartbeat pulsing across the light years. To understand this phenomenon, you first have to picture the orbital dance. Many of these massive binaries don't trace perfect circles around each other. Their paths are elliptical, meaning their distance from one another constantly changes. At the point of closest approach, known as periastron, the gravitational forces between them become exceptionally strong. This is the moment of the heartbeat. As the stars swing perilously close, their immense gravity doesn't just pull, it literally distorts their shapes. Each star, which would be a perfect sphere if alone, is stretched into a football-like ellipsoid by the tidal pull of its companion. This tidal distortion is the key to the heartbeat pulse. When the stars are at their closest, they present their elongated, distorted faces to us. This change in shape alters the amount of surface area visible from Earth, which in turn affects their combined brightness. Furthermore, the same intense gravity that distorts the stars also causes what are known as tidal oscillations, actual quakes rippling across the stellar surfaces, much like the ocean tides on Earth but on a cataclysmic scale. The combination of this changing surface area and these energetic oscillations creates a sharp, brief increase in brightness right at periastron, followed by a rapid return to normal as the stars swing apart again. It's a direct, observable consequence of gravity flexing the very bodies of the stars themselves. This heartbeat is far more than just a pretty light show. It is one of the most powerful tools in an astronomer's kit for stellar forensics. Because the heartbeat occurs at a specific, predictable point in a perfectly measurable orbit, it provides an exquisitely precise clock and ruler for the system. From the timing and depth of the eclipses and the heartbeat pulses, astronomers can calculate the orbits of the stars with incredible accuracy. They can determine the exact masses of the two stars, a fundamental property that is notoriously difficult to measure for single stars. This is the gold standard for weighing stars. By analyzing the subtle ways the light changes during the tidal distortions, they can even probe the internal structure of the stars. The way a star responds to being squeezed and stretched by its partner's gravity depends on how mass is distributed within it, whether it has a dense, compact core and a diffuse envelope, or a more evenly distributed structure. The heartbeat, therefore, acts like a sonogram for the star, allowing us to see inside it and understand its internal density and composition without ever having to visit. The discoveries from these systems have been revolutionary. They have confirmed theoretical models of stellar structure with real-world data, showing that our understanding of how mass and pressure balance inside a star is fundamentally correct. They have also revealed surprising phenomena, such as the way the intense tidal forces can drive massive mixing within the stars, churning up material from the core and bringing it to the surface, which can dramatically extend the star's life and alter its chemical signature. In a very real sense, these binary systems are natural laboratories, allowing us to conduct experiments in stellar physics that we could never replicate on Earth. Each heartbeat pulse is a data point, a precise measurement that helps us refine our models of how stars live, interact, and evolve together. This rhythmic celestial dance, once a curious pattern in a graph, has become a foundational method for unlocking the secrets of mass, gravity, and structure that govern the lives of the universe's most magnificent giants. Yet even the violent transformations of Wolf-Rayet stars and the rhythmic heartbeats of binary systems cannot capture the full complexity of stellar evolution, which brings us to a class of celestial objects so transitional and fleeting they are essentially caught in the act of becoming something else entirely. These are the OFF/WN9 stars, enigmatic hybrids that defy easy classification, behaving as if they can't decide whether they are brilliant of supergiants or exposed Wolf-Rayet stars. To understand their peculiar nature, we must first picture the two identities they straddle. An of supergiant is a true stellar aristocrat, a massive, hot, blue star whose spectrum is dominated by intense emission lines from ionized nitrogen and helium, signs of a powerful stellar wind beginning to strip away its outer layers. On the other side is the WN star, a Wolf-Rayet subtype that has already shed its hydrogen envelope entirely, revealing a searingly hot core and unleashing a hurricane of a stellar wind. The OFF/WN9 star exists in the no-man's land between these two states, a celestial waystation where a star is no longer a pristine blue giant but not yet a fully unveiled Wolf-Rayet. It is a star caught mid-undressing, and its brief, unstable existence provides a crucial missing link in the life story of the most massive stars. A perfect and breathtaking example of this transitional state is the legendary Pistol star, located near the chaotic center of our Milky Way galaxy. This object is a true hypergiant, believed to have been born with a mass well over 100 times that of our Sun. What makes the Pistol star so fascinating is its spectral signature, a confusing mix of features that had astronomers debating its nature for years. Its spectrum shows strong, broad emission lines of helium and nitrogen, characteristic of a Wolf-Rayet star, but it simultaneously reveals the presence of hydrogen lines, which should be absent in a classic WN star. This hydrogen is the telltale clue. It means that while the pistol star is losing mass at a prodigious rate, ejecting the equivalent of an Earth mass every few years, it has not yet completely blown away its hydrogen-rich outer shroud. It is in the process of transforming from an supergiant, which still holds onto its hydrogen atmosphere, into a hydrogen-poor WN Wolf-Rayet star. This metamorphosis is not a gentle one. It is a violent, continuous shedding driven by the star's radiation pressure teetering on the edge of the Eddington limit, pushing its atmosphere outward in a desperate, ongoing struggle against its own gravity. This profound transition is graphically illustrated by the star's position on the Hertzsprung-Russell diagram, the fundamental map of stellar astronomy. While a typical supergiant sits firmly in the hot, luminous blue region, and a classic WN star is found in an even hotter domain, OFF/WN9 stars occupy an intermediate zone. They are slightly cooler and more evolved than their supergiant progenitors, but not as hot and exposed as the WN stars they will become. This shift in position is a direct result of their ongoing mass loss. As the star relentlessly blows its outer layers into space, it effectively peels back its own surface, revealing deeper, hotter layers that were previously hidden. This causes the star's apparent surface temperature to increase and its spectral type to shift, moving it steadily leftward across the HR diagram. The OFF/WN9 phase represents a specific, critical point on this journey, a moment when the star is halfway through this process of self-revelation. It is a brief, volatile chapter that might last only a few tens of thousands of years, a mere instant in cosmic terms, making these stars rare and precious snapshots of stellar evolution in real time. The significance of identifying and studying these transitional objects cannot be overstated, as they act as vital calibration points for our models of how the most massive stars live and die. They confirm a direct evolutionary pathway. A massive O-type star evolves into an supergiant, which then passes through the OFF/WN9 phase as it sheds its hydrogen envelope, finally emerging as a hydrogen-free WN Wolf-Rayet star before its inevitable core collapse. Without these transitional objects, the link between these stages would be largely theoretical. By analyzing their powerful stellar winds and the chemical composition of their ejected material, we can measure the precise rate at which a star dismantles itself. This allows astronomers to refine their predictions about the final mass of the star's core just before it goes supernova, which in turn determines whether the death explosion will be a relatively ordinary supernova, a gamma-ray burst, or even a direct collapse into a black hole. The OFF/WN9 stars are the missing pieces in our stellar genealogy charts, providing observational proof that the universe's greatest giants spend their final millennia in a continuous, dramatic, and self-imposed transformation, sculpting their own destinies with every gust of their colossal winds. But while the transformative winds of BE supergiants are confined to elegant disks, the universe also hosts stars that unleash their fury in a far less structured and more devastatingly comprehensive manner. This is the domain of the solar system destroyer winds, a relentless, isotropic bombardment that would erase the delicate conditions for life as we know it. To grasp the sheer power of these stellar hurricanes, we can look to the legendary variable star P Cygni, a hypergiant whose name has become synonymous with this particular brand of cosmic violence. P Cygni is losing mass at a rate that is almost incomprehensible. Every single year, it ejects approximately 1/1,000,000th of a solar mass into the void. That might sound like a tiny fraction, but it translates to the star blasting away the equivalent of our entire Earth every 3 years. Project that forward, and in the span of just 10,000 years, a blink in cosmic time, P Cygni would have shed a total amount of mass equal to our entire Sun. This isn't a gentle breeze, it's a continuous supersonic exhalation of the star's own substance, a desperate attempt to stabilize that carves a permanent scar on the surrounding interstellar medium. Now let's conduct a terrifying thought experiment. Imagine if our own familiar, life-giving sun were instantly replaced by a star like P Cygni. The change would be immediate and apocalyptic, unfolding in a sequence of horrifying events. The first and most visceral impact would be the sheer, unadulterated brightness. A star like P Cygni can be over 500,000 times more luminous than our sun. Appearing in our sky, it wouldn't just be a brighter sun. It would be a physical presence, a searing white furnace whose light would feel like a physical weight. The increase in visible light alone would be enough to scorch the Earth's surface to a crisp, incinerating all life in a matter of moments, but the visible glare would be the least of our problems. The true killer would be the torrent of high-energy ultraviolet radiation. Our current sun emits a modest amount of UV light, most of which is thankfully blocked by our planet's ozone layer. A P Cygni-type star, however, is a prolific producer of extreme ultraviolet and even soft X-ray photons. This intense high-energy flux would act like a cosmic sandblaster, striking the atmospheres of every planet in the solar system. For a world like Earth, it would first shatter the protective ozone molecules, and then begin systematically breaking apart the bonds of nitrogen and oxygen molecules in the air itself. Over a relatively short period, our thick, life-sustaining atmosphere would be literally boiled away into space, molecule by molecule, leaving behind a barren, irradiated rock not unlike Mercury. Simultaneously, the physical wind from this new star would begin its destructive work. The solar wind from our sun is a tenuous stream of particles that interacts gently with planetary magnetic fields to create beautiful auroras. The wind from a P Cygni like hypergiant is a different beast entirely, a dense, supersonic plasma traveling at thousands of kilometers per second. When this hypersonic gale reached Earth, it would not produce a light show. It would overwhelm our planet's magnetic field in an instant. Our magnetosphere, the protective bubble that deflects the solar wind, would be compressed and stripped away, leaving the planet's surface fully exposed to the direct onslaught of the stellar blast. The physical pressure of the wind would begin to erode the planetary surface itself, and the relentless flow of charged particles would bathe everything in a lethal bath of radiation. The oceans would be torn away, and the very rock would begin to ablate under the ceaseless cosmic torrent. Within a geologically short time frame, Earth would be utterly sterilized and transformed into a desiccated husk. The destructive influence of such a star, however, extends far beyond its immediate planetary system. The relentless outward pressure of its wind, combined with the intense radiation field, acts like a cosmic plow, pushing against the thin gas of the interstellar medium. This creates a vast, inflated cavity known as an astrosphere, but on a scale that dwarfs our own sun's heliosphere. Around a star like P Cygni, this bubble of hot, shocked wind can stretch for hundreds of light-years across. Within this colossal volume, the normal, gentle conditions of interstellar space are completely overturned. The powerful shock front at the bubble's edge compresses any interstellar clouds it encounters, potentially triggering new star formation in its wake, while also clearing out a region so effectively that it would prevent nearby planetary systems from ever forming in the first place. The star becomes the dominant architect of its local galactic environment, a tyrannical ruler whose very existence obliterates the possibility of serene, life-nurturing solar systems like our own for an immense distance in all directions. This is the ultimate legacy of a star with solar system destroyer winds. It is not merely a bright light in the darkness, but an active, violent force that reshapes its entire cosmic neighborhood, ensuring that its reign is one of magnificent, absolute, and sterile dominion. After witnessing the spectacular finales of stars that light up the galaxy, it's almost unsettling to consider a fate that is the complete opposite. a death so quiet and dark that it defies our very definition of a stellar end. This is the realm of silent black hole formation, a theoretical process where a supermassive star skips the supernova stage entirely and simply vanishes from the visible universe, leaving behind no brilliant explosion, no expanding nebula, and no observable signal to mark its passing. It is a stellar death that occurs behind a cosmic curtain, a final act of collapse so total and efficient that the star is erased from the sky without a trace. The key to this silent disappearance lies in a failure of the very mechanism that creates a supernova. In a standard core collapse event, when the iron core of a massive star becomes too heavy to support itself, it implodes at nearly a quarter the speed of light. This collapse is so violent that it squeezes protons and electrons together to form neutrons and neutrinos. For a brief, critical moment, the core becomes an incredibly dense neutron star, and the energy released in the form of a tremendous neutrino blast along with a rebounding shockwave is what tears the star apart, blasting its outer layers into space in a supernova. But for the most massive stars, those with initial masses perhaps above 25 solar masses, this rescue mission can fail. The core of such a star is so tremendously heavy that the force of its own gravity becomes insurmountable. When it collapses, the newborn neutron star at its center is immediately too massive to be stable. The pressure from the outward streaming neutrinos, which in a smaller star would help drive the explosion, is simply not enough to overcome the immense gravitational pull. Instead of rebounding, the collapse continues unabated. The neutron star itself is crushed in a fraction of a second into a point of infinite density, a black hole. There is no bounce, no shockwave, and therefore no supernova. The entire stellar envelope, which was waiting for a signal to be ejected, instead finds its support yanked away. With nothing to stop it, this vast shell of gas simply falls inward down the gravitational well and is swallowed by the newborn black hole. Observing such an event would be a profound challenge. Instead of a brilliant months-long optical transient that outshines its host galaxy, you might witness only a brief, faint flicker. As the star's outer layers are cut off from their energy source and plunged toward the event horizon, a small amount of material could be ejected through complex hydrodynamic processes or could form a brief, faint accretion disk, producing a low luminosity optical flare. But this would be a pitifully dim event compared to a true supernova, perhaps only 100th or 1,000th as bright. It might be mistaken for a minor stellar outburst or an unusual transient in a distant galaxy, easily overlooked by all but the most dedicated surveys. For all intents and purposes, from our vantage point billions of light years away, the star would just wink out of existence. It would be present in one image of a galaxy and absent in the next, with no spectacular fireworks to explain its departure. This theory of direct collapse offers an elegant solution to the long-standing red supergiant problem, where pre-explosion images of galaxies show a perplexing absence of progenitor stars for supernova, originating from stars born heavier than about 18 solar masses. It suggests that these missing giants aren't missing at all. They are simply dying in the dark. Their final moments are not a blaze of glory, but a swift and final descent into oblivion. The existence of these silent deaths would also have significant implications for the population of black holes in the universe. It would mean that a certain fraction of black holes, particularly the more massive ones, are born without the violent, explosive kick that a supernova imparts. This could leave them in quieter orbits within binary systems or star clusters, influencing the dynamics of their environments in ways that are distinct from black holes born from noisy supernova. The silent collapse is the ultimate cosmic stealth mission, a process that ensures the universe's most massive stars can end their lives not with a bang, but with the faintest of whimpers, leaving behind only a dark, gravitational monument where a brilliant giant once shone. Now, let's journey back in time to the very dawn of the cosmic story. to an era so profound that its transformation set the stage for everything we see in the night sky today, the epoch of reionization. For hundreds of millions of years after the Big Bang, the universe was a very different place, plunged into what astronomers call the cosmic dark ages. It wasn't dark because there was no light, but because space was filled with a thick, soupy fog of neutral hydrogen gas. In this primordial mist, light couldn't travel freely. Photons from the first luminous objects would almost immediately be absorbed by a hydrogen atom, only to be re-emitted in a random direction, trapped in a cosmic pinball game. The universe was an opaque, featureless veil, and if you could have been there with a telescope, you would have seen absolutely nothing in any direction. This great shroud persisted until a new kind of power emerged to tear it apart, and that power came from the first generation of stars, the legendary, and still mostly hypothetical, population Roman 3 stars. These weren't just the first stars, they were the universe's pioneer giants, forged from the pristine hydrogen and helium left over from the Big Bang, utterly devoid of the heavier elements that came from later stellar generations. Because they lacked the metals that help cool gas clouds and allow them to fragment, theory suggests these population Roman 3 stars were almost unimaginably massive, likely ranging from 100 to over 1,000 times the mass of our Sun. Imagine the sky filled not with the gentle, familiar points of light we know, but with colossal, searingly hot blue behemoths, each one a supermassive star in its own right, living ferociously bright and dying explosively young. The ultraviolet radiation pouring from these stellar titans was the key that unlocked the universe. A star like our Sun emits a relatively modest amount of high-energy ultraviolet light, but a population Roman 3 star, with its tremendous mass and surface temperature, would have been an ultraviolet cannon. Its photons were so energetic that when they slammed into the ubiquitous neutral hydrogen atoms, they didn't just bounce off, they delivered a knockout blow. Each ultraviolet photon carried enough energy to rip the electron right off its proton, a process known as ionization. It was a cosmic battle of light against matter, and for the first time, light was winning. As more of these brilliant giants ignited across the cosmos, they began to carve out ever-growing bubbles of ionized plasma within the neutral fog. Think of it like frost retreating across a window pane as sunlight hits it, with clear patches slowly expanding and merging. Inside these bubbles, the universe became transparent. Light could finally travel in a straight line for millions of light years. The photons that had been trapped for eons were suddenly set free, and the dark ages were finally coming to an end, not with a whimper, but with the brilliant, coordinated flash of countless supermassive stars turning on the lights for the entire cosmos. This was not a quick, single event, but a gradual, patchy process that unfolded over several 100 million years. Different regions of the universe ionized at different times, depending on when the first stars and galaxies formed there. Dense knots of matter, where gravitational collapse happened first, became the hotspots of reionization, launching their ionizing bubbles earlier and seeing their clear regions grow larger. The process was likely completed by around 1 billion years after the Big Bang, leaving the vast intergalactic medium, the space between galaxies, as the incredibly thin, highly ionized plasma that it remains today. This fundamental transition is one of the most important in cosmic history because without it, the universe would still be an opaque fog. We would not be able to see distant galaxies or quasars. Our telescopes would peer out into a featureless wall of glowing hydrogen. The very act of observational cosmology, of looking back in time to understand our origins, depends entirely on the fact that these first supermassive stars performed this crucial service, burning away the cosmic haze and creating the transparent universe we now call home. The legacy of these pioneers, however, goes far beyond just clearing the fog. Their incredibly violent deaths as pair-instability, supernova, or direct collapses into black holes seeded the early universe with the first heavy elements. This metal's pollution, while tiny at first, was absolutely essential for the next chapter of cosmic evolution. It allowed subsequent generations of stars, population Roman II, and eventually our own population I Sun, to form from slightly enriched gas. This enrichment allowed gas clouds to cool more efficiently and fragment into smaller, more stable stars, including the long-lived, low-mass stars that are still shining today. Furthermore, the supermassive black holes that may have formed from the direct collapse of the very largest population Roman III stars are the leading candidates for the seeds of the supermassive black holes we now find at the centers of nearly every galaxy, including our own Milky Way. So, the role of these first supermassive stars was truly twofold. They were both the universe's first great illuminators, ending the Dark Ages and making the cosmos observable, and its first great chemists and architects, providing the raw materials and the gravitational anchors for everything that would follow. Their brief, spectacular lives fundamentally shaped the architecture of the cosmos, proving that even the most fleeting of giants can leave a permanent mark on the fabric of reality. But if the first stars pushed the boundaries of mass, what about the true heavyweights we can observe in our cosmic backyard today? This brings us to the final frontier and one of the most exhilarating questions in modern astrophysics. Just how big can a star actually get? For decades, the theoretical upper limit was thought to be around 150 solar masses, a boundary set by the very radiation the star produces. Beyond this point, the incredible luminosity from a star's core should generate so much outward radiation pressure that it would literally overwhelm the star's own gravity, blasting its outer layers into space and preventing it from growing any further. This is the Eddington limit, a fundamental check on stellar ambition. Yet, when we point our most powerful telescopes toward regions like the Tarantula Nebula in the Large Magellanic Cloud, and specifically at the dazzling star cluster R136, we find objects that seem to be openly defying this rule. Stars like R136A1, the current record holder, stagger the imagination. Current estimates suggest it was born with a mass of somewhere between 250 and 320 times that of our Sun. It's a stellar Goliath that forces us to reconsider the very engines of star formation and stability. So how does a star like R136A1 even form without immediately tearing itself apart? The secret lies in the absolute frenzy of its birth environment. R136 isn't a quiet stellar nursery. It's a dense, chaotic starburst cluster, a cosmic mosh pit where gas clouds are colliding and collapsing under their own weight at an astonishing rate. In such a maelstrom, the accretion of material onto a growing protostar can happen so rapidly, in a process called competitive accretion, that the star can bulk up to an extreme mass before its own radiation has a chance to switch off the inflow. It's like building a skyscraper so quickly that the wind doesn't have time to blow it over during construction. Furthermore, the sheer density of the cluster might play a role in temporarily containing the fierce radiation pressure. And once it's ignited, R136A1's own composition offers a clue. It's extremely metal-rich compared to the first stars, meaning its atmosphere is filled with heavy elements. These elements are exceptionally good at absorbing light, which actually makes the stellar wind more opaque. This might sound counterintuitive, but a more opaque wind can be more efficient at converting radiation pressure into mechanical force, allowing the star to shed mass in a more controlled, albeit still tremendous, outflow rather than experiencing a single catastrophic disruption. It walks a razor's edge, balancing on the very limit of what is physically possible, using its own complex physics to hold itself together just long enough to live its brief, spectacular life. The ultimate fate of such an incomprehensible object is as dramatic as its birth. For stars in this extreme mass range, between approximately 130 and 250 solar masses, the pair-instability supernova awaits, a total annihilation that leaves no remnant. But for the true monarchs, the stars pushing toward 300 solar masses like R136A1, the end could be even more absolute. Their cores are so immense and generate such ferocious temperatures that the production of electron-positron pairs might occur so rapidly and efficiently that it triggers a collapse of unprecedented violence. This wouldn't be a mere explosion, it would be a complete disintegration of the star's entire structure. Some models suggest that for these ultra-massive stars, the pair-instability process could be so effective at removing pressure support that the entire star, not just its core, collapses inward almost uniformly, leading to the direct formation of a massive black hole without a visible supernova at all. It would be the silent death of a giant, a final act of cosmic stealth. Alternatively, the explosion could be a pair-instability event on steroids, a hyper-explosion that not only vaporizes the star but in doing so, unleashes so much energy that it might temporarily outshine its entire host galaxy, becoming for a few weeks the brightest single object in the observable universe and blasting heavy elements across intergalactic space. The existence and behavior of these colossal stars are more than just a record-breaking curiosity. They are fundamental probes of the most extreme physical conditions the universe can concoct. By studying R136A1 and its peers, we are effectively stress-testing our theories of hydrodynamics, mass loss, and nuclear fusion under conditions we can never hope to replicate on Earth. They serve as critical anchors for our understanding of how the first stars, the population Roman III behemoths, must have lived and died, shaping the early cosmos. Furthermore, the black holes they leave behind are the likely seeds for the supermassive black holes that now lurk in galactic centers. Each one of these stellar titans is a natural laboratory, a cosmic crucible where matter is pushed to its absolute limits. Their brilliant, violent lives and their decisive, monumental deaths represent the final word in stellar evolution, the ultimate expression of how gravity and fusion can conspire to create objects of such terrifying power and majestic beauty that they forever expand our understanding of what is possible in the universe. So as we've journeyed from unstable hypergiants vomiting their own atmospheres into space, to stars that stage supernova previews and then simply survive, to the furious, spinning engines of magnetars and gamma-ray bursts, one thing becomes overwhelmingly clear. The lives of these stellar titans are a symphony of chaos and beauty on the grandest scale imaginable. They are not merely larger versions of our own sun. They are fundamentally different beasts operating under a set of physical laws pushed to their absolute breaking point. From the frantic identity crises of luminous blue variables to the self-cannibalizing winds of Wolf-Rayet stars, and from the deceptive dimming of Eta Carinae borealis variables to the silent, dark collapse into a black hole, each behavior is a testament to the incredible diversity of stellar death and transformation. These aren't just random oddities, they are critical chapters in the life story of the most massive objects the universe can forge, each one a unique expression of the cosmic battle between gravity and radiation, between creation and destruction. The significance of this wild menagerie of behaviors extends far beyond mere celestial spectacle. These stars are the universe's ultimate alchemists and architects. It is within their searingly hot cores that the fusion of elements like carbon, oxygen, and silicon takes place, and it is in their violent supernova deaths that even heavier elements, like the gold in your jewelry and the uranium in the Earth's crust, are forged and scattered across the galaxy. They are the primary source of the heavy elements that make up our planets and our very bodies. Furthermore, as we saw with the green P galaxies, the collective fury of these stars can ionize entire galaxies and drive the large-scale evolution of the cosmos, just as the first population Roman III stars did when they burned away the primordial fog of the Dark Ages. Their powerful winds and explosive death shaped the interstellar medium, triggering new rounds of star formation and seeding the cosmos with the dust that will one day coalesce into new planets. In a very real sense, to study these supermassive stars is to study our own cosmic origin story, tracing the lineage of the atoms that constitute our world back to the heart of a long-dead giant. Ultimately, the bizarre and often violent behaviors of these stars are not simply quirks. They are the key that unlocks our understanding of the most extreme processes governing the cosmos. They serve as natural laboratories for physics under conditions we could never hope to replicate on Earth, allowing us to test our theories of gravity, nuclear fusion, and matter itself at the very edge of known science. Every strange pulse, every runaway star, and every silent collapse provides a crucial data point, refining our models and deepening our comprehension of how the universe works at its most fundamental level. They challenge our assumptions, force us to revise our textbooks, and remind us that the universe is far more inventive, dynamic, and wondrous than we often give it credit for. The next time you find yourself under a clear, dark sky, take a moment to look up at the familiar constellations. Remember that nestled within that sea of twinkling lights are these true celestial titans, stars living lives of such extreme drama and grandeur that they defy easy imagination. They are out there right now, some erupting, some spinning at breakneck speeds, some quietly building toward a cataclysm that will one day seed future worlds with the stuff of life. Their stories are still being written, and ours is inextricably linked to theirs. If unraveling these cosmic mysteries sparks your curiosity, be sure to subscribe and hit the notification bell, as we have many more deep dives into the universe's greatest wonders coming your way. The cosmos is full of secrets waiting to be discovered, and together we can continue to explore